Hey everyone, and welcome back to PrepFusion. So in this video we will be covering two topics from power system analysis, that is uh, the power factor improvement, voltage controlling techniques, and obviously the economic load dispatch. This will be roughly of 6 hours of content, and in this 6 hours you can expect roughly around 2 marks, right? And these are very simple topics. It will feel like you already know most of the stuff. Whatever I will teach here, you will already be knowing most of this stuff. You just need to study. Economic load dispatch is a new topic, I do agree, but it's very simple, very easy topic, and every year they're asking one question from this economic load dispatch. So that's why I thought of uploading it on YouTube, because it is a very important topic and a very scoring topic, so you guys can benefit from it. So of course, before this video there are already three marathons, right, of fault and stability. And then there is sorry, these are the fault marathons. There is a power system stability marathon as well, and of course there is a uh, fifth marathon, that is the power system performance of power system transmission lines. So make sure you cover those, right? And you can cover this one directly as well, because this is kind of a separate topic which is not that related, but again very important topic, because you can expect 2 marks that can be asked in the gate examination. So yeah, if you are enjoying this video, like the video, comment down below whatever part you enjoyed the most, hype the video, and let's begin with voltage controlling techniques. Hi everyone, and welcome back to PrepFusion. I'm Anish, and today we will start with the lecture 29 of PSA 1. So today we will discuss about power factor improvement. So how can we improve the power factor, and why the improvement of power factor is important. So before starting uh, with power factor improvement, let's understand what is power factor. What is the definition of power factor? So definition of power factor, cos phi, right? Power factor is known as cos phi. That is simply the active power delivered to the load upon the reactive power. Okay, that is what my power factor is equals to. Now uh, let's take a inductive load, and in that kind of load we will discuss what is the power factor. Basically your most of your loads, right, actual loads in industry will be inductive. Your fan, everything mostly will be inductive. Hardly there will be few capacitive loads. Okay, so with that in consideration we will derive everything. So our load is inductive. You know, when load is inductive, what kind of reactive power it demands? So if load is inductive, it demands inductive reactive power. Okay, inductive reactive power. Okay, so now what is the power? So power factor is this. How can I calculate over here what is the power factor? So we know what is the active power that is absorbed in this load, that is I square R, right? So active power absorbed in this load will be I square. Sorry, it is not active power upon reactive power, it is active power upon apparent power. Apparent power, I'm really sorry, active power upon apparent power, right? So the active power is I square into R. And what is the apparent power? Apparent power is nothing but the product of voltage and current across the load. So my voltage is this and the current is this I, right? So apparent power is product of voltage into current, and remember this is the magnitude of current. Basically it is the magnitude of voltage into magnitude of current, because things are complex over here, and this will be magnitude of I whole square into R. Okay, magnitude of I whole square into R. Now if I replace it over here, right, in the formula cos phi, it comes out to be magnitude of uh, magnitude of I whole square into r divided by magnitude of v into magnitude of I, which is equals to magnitude of I into r divided by magnitude of v. What is magnitude of v divided by magnitude of I? That is simply equals to z, right? Magnitude of z is simply magnitude of v upon magnitude of I. So this will be r by z. For a series circuit, we know this, it is r by z. So if I draw the power triangle, basically, sorry, not the power triangle, the impedance triangle. So my resistance will be real, my reactance will be imaginary jxl, right, and this will be my impedance, magnitude of z, and this will be the angle phi z. So this is called as the impedance angle. Okay, power factor angle and impedance angle are magnitudes are same, but sign will be opposite. Okay, sign will be opposite, but magnitudes will be same. Okay, now what else can I say? So my power factor is either you can say it is equals to r by z for a simple series circuit, or you can say cos phi. If I want to write in terms of power and apparent power, it will be p by s. Now if I draw the power angle, so this was the impedance triangle. We know the power triangle will be what? Active power will be along x axis. Then I will have the lagging reactive power, that will be plus jq receiving it, and right, let me assume that as plus jq receiving it, that's why it is at positive clockwise direction, and this, right, will be my apparent power, that is magnitude of s, and this will be my angle phi. So cos of this angle phi will be equals to my power factor. Okay, sorry, impedance angle and your power factor angle will be opposite. This we have learned in phasor, so basics of network theory. Okay, I will not explain it over here. So now one more formula we can derive. What formula we can derive? So my cos phi is p by s, right? P by, this is the p and this is the s. What about tan phi? What is tan phi? Tan phi will be hypotenuse upon the base. So tan phi is hypotenuse, that is q upon the base, that is p. So what I can observe, the reactive power actually can be controlled with p tan phi, and this will be used later on. Okay, we will use this formula. So reactive power formula comes out to be q tan phi, and this will be valid in any circuit, because just like your power, right, power is s cos phi is always valid, this also will be always valid, no matter what is the circuit, series or parallel. But for a series circuit, this will be valid. Okay, if it's a parallel circuit, then you have to calculate. Okay, these are the things that you need to keep in mind. So your reactive power, we can say your active power is vi cos phi. It is also sometimes called as vi cos phi. Okay, so which sometimes for a series load it is I square r, for a series load, simple series RL load. Now what about the reactive power? Reactive power Q will be reactive power Q will be Vi sin phi. Okay, so which will be for a series RL load, it will be I square into XL. That will be my lagging reactive power. Okay, so these we will use later on, and your power factor, remember, always will lie between the range of 0 to 1. These are the things that we will use in this chapter. So I am just summarizing and revising everything, whatever you already know. These things I hope you already know. Okay, now let's do a very basic question, and from there understand this concept even better. That can you pause the video and try what is the active and inductive reactive power delivered to the load by the supply? Okay, how do I find out the active and inductive power delivered? So this, right, is given in terms of z angle theta, right? So I will assume it to be a series RL load because theta z is positive. If theta z is positive, that means it is an inductive load. That's why it is inductive load. So it will absorb the inductive load. So my z is this, right? And my what will be my cos phi? It will be simply cos of theta z. Magnitude will be same, cos of theta z. Cos theta z. So it will be cos of 60 degrees. Okay, so which will be cos half. Okay, so power factor is half. What is the power delivered? So I know the voltage. Can I find out the current? Yes, current also I can find out. Current will be voltage upon the impedance, that is z angle theta, that is 10 angle 60 degrees. So it will be 24 angle minus 60. So that's why this is the actual angle phi, right? And this is the theta z. Theta z and phi are opposite to each other. I hope you remember all these things. But their cos right will be same. Cos of minus 60 and cos 60 will be same. That's why I wrote here cos of theta z and cos phi will be same. Okay. So current is this. So what will be the active power? Active power will be equals to Vi cos phi, which will be 240 into I is 24 into cos of 60, that is half. So it will be equals to 120 into 24. 120 into 24. Just give me 1 second. 120 into 24 into 24, which is divided by 2, or divided by 2 is already there, which is 28880. Can we verify the other formula as well? What was the other formula? Magnitude of I square into R. So what is magnitude of I square into R? So magnitude of I already know. What is R? R will be, if I assume it to be a series load, right? R and XL. So my R will be simply Z cos theta Z, right? From this triangle, from this impedance triangle, my R will be Z into cos of theta Z or phi Z, whatever you want to say. So this will be equals to Z of cos theta Z 10 cos of theta Z, that is half. So this will be 5 ohms. Okay, this will be 5 ohms. So R will be 5. So I square, that is magnitude of 24, like 24 whole square into 5. What is it equals to? 24 whole square into 5. It is the same value, that is 2880. So it will come out to be same. Now what is the reactive power delivered? So reactive power delivered will be Vi sin phi. Q will be Vi sin phi, or you can say P tan phi. All formulas, like we'll just verify all the formulas. Okay. So Vi sin phi. So here actually the angle is pretty important. Okay. So sin Vi of sin 60. So it will be 240 into current is 24 into sine of 60, sine of 60 degrees. So this will be 240 into 12. Okay, which will sorry, sine 60 is root 3 by 2, actually not 12, sorry. This will be 12 root 3. So this value will be 240 into 12 root 3, that is 28880 root 3. Now one mistake I had made here when I told you that theta z and phi are not equal. For a for a series circuit actually theta z and phi are equal. What is phi basically? Phi, if you remember, right, there was a formula of apparent power that was equals to Vi conjugate, right? So V will have its angle V angle theta V, and I will have its angle theta I, but I need to take the difference of this, right, because it is a conjugate. So ultimately this will come out to be magnitude of V, magnitude of I, angle of theta V minus theta I. So your power factor angle phi is actually theta V minus theta I. Okay, so in this case it is same as the impedance angle. Actually I made a mistake, it is same as the impedance angle. For admittance it is the opposite, admittance angle and the power factor angle are opposite, I am sorry. So this will be equal actually. Here also this will be, power factor angle will be not, this will not be minus 60, actually power factor angle will be plus 60 only. Okay, that's my bad. So here it comes out to be positive reactive power 2880. Let's now verify the other formula. What was the other formula? Other formula was I square into x. Okay, I square into x. I square into x will be equals to 24 whole square into the inductive reactance, that is, what will be the inductive reactance? X will be equals to z sine theta z, right, which is equals to simply 5 root 3. Theta z is 60 and z is 10, magnitude of z is 10. So 5 root 3, which comes out to be same, which will come out to be same only, which is 2880 root 3 VAR, same as the previous one, right? Okay, I hope the formulas I hope are verified. Now we want to do one interesting experiment. Let's say I have a VAR compensator here that delivers, like they are telling in the question, that it is delivering 1250 VAR to the load. Okay, basically it is delivering this much amount of reactive power to the load. Now they are asking what is the current delivered to the load by the supply. What will be the current delivered by the supply? Basically that is what they are asking. What is the current delivered? So what is the current delivered? How will I find it out? So this reactive power formula can also be found out from this formula, right? Another formula was there for reactive power, that was Q was equals to P tan phi. So P will be equals to P we have found out, that is 2880, right? What is tan phi? Tan 60. Tan 60 is how much? Root 3. So it will be 2880 into root 3 VAR. Okay, 2880 into root 3 VAR. So yeah, that I hope that is clear. Now here, right, this is delivering 1250 VAR. So what will be the load current? How will I find out the load current? So what is the demand of this load? The demand of this load, if I am applying a voltage of 240 volts, if the voltage is fixed, the demand of this load is, what is the PL? PL is 2880 VR. PL is this much watt, right? And QL, the inductive reactive power demand, is 2880 root 3. Okay. Now out of this amount of reactive power, actually my VAR compensator is delivering 1250 reactive power. So how much power will the supply send? The supply will send same power as the load power, because VAR compensator is not delivering any active power, it is only delivering reactive power. So 2880 and reactive power will be QS, will be whatever the demand is, right, minus the whatever the VAR compensator has already sent. So this much amount of reactive power I don't need to send, VAR compensator has already delivered this much amount of reactive power. How? We will explain in the next few slides how it happens. Okay, that we will understand later on. So the amount sent by the supply will be the demand minus the amount already sent to the load, that is 1250 VAR, which will be equals to 4988.3 minus 1250. Okay, 3738.3. This is the amount of VAR that the supply will set. Now what is the total apparent power? Apparent power will be PS plus JQS, which is equals to 2880 plus J3738.3. Okay, now I know this formula for apparent power. Magnitude of apparent power is simply magnitude of the voltage into magnitude of the current, right? So from here my magnitude of the current will be magnitude of the apparent power, that is 2, whatever is the magnitude, I will calculate the magnitude, whole square plus 2880 whole square whole under root. So this will be 4719 divided by the voltage, that is 240. Okay, this is 19.66 amperes. And previously what was the current? Previously, if you see, the current was 24, magnitude of the current here was 24 amperes, right? So there is an advantage here, the current got reduced. If the current got reduced, then what happened is that the losses magnitude, because this current will flow through the whole line, then only it will reach here, and we know transmission line is very long. So if I am able to connect a VAR compensator near the load, then I don't need to supply this additional current due to the reactive power, only mainly it will deliver the active power. Okay, that is the advantage. Now whatever power factor we discussed, right, this was the load power factor. I have told you the sending end power factor will be what? Sending end power factor, this we have discussed previously, is the active power by the sending end by the apparent power by the sending end. That is what my sending end power factor is. So here what was my sending end power factor? Like this, right? This was the load power factor. This is whatever we discussed. This is the load power factor, right? Load power factor. It is at the load. What is the sending end power factor? The sending end power factor is the power sent by the voltage source divided by the apparent power. Okay, divided by the apparent power. Now right, what is the power delivered? Power here, right, in this case there is no other circuitry in between. Whatever the power this is absorbing, the same power I am delivering for both the reactive and active power. There is no device here, right? So it will be simply same as PL by Q SL, which will be simply here, right? We have already discussed the active power is 2880 and the reactive power will be, sorry, and the apparent power will be 2880. Reactive power is this root 3, right? If I take the mod of this, square this and this one and take the mod, then basically what will come out to be, it will come out to be 2. You do it, it will come out to be 2. So this will be 1 by 2 basically. So my phi s will come out to be 60. So here phi s and the phi l are same. Load power factor and the sending end power factor and the receiving end power factor are the same. Now what if here what is the sending end power factor? Receiving end power factor is same, cos phi l or cos phi r. Receiving end power factor is same, that is 0.5. Okay. So what is the sending end power factor? Sending end power factor is 2880 by the apparent power. Apparent power is 4719, right? Magnitude of apparent power is 4719. So 2880 divided by 4719, so it comes out to be 0.61. So you see the power factor has improved. Although the load had a power factor of 0.5, this has a power factor of 0.61. Higher the power factor, better it will be, because of course the same thing, right? Same formula I will show you. My current, magnitude of current depends on the power delivered by V cos phi. So we know the power delivered will be constant, voltage is constant, right? Power delivered to the load will be constant. No one will deliver the additional power. Supply will only deliver the active power. So I need to improve the power factor. So power factor I need to increase. If I increase, the magnitude of current will go down. So here I see power factor has increased. So that is the advantage of these kind of circuits. So would I have been able to calculate this in a better manner? So this was the reverse engineering. But in question, what will they ask? They'll ask you, tell me the amount of reactive power the VAR compensator need to deliver. I'm just writing the rough question for making the power factor cos phi to 0.61. From 0.5 I need to improve it to 0.61. What is the amount of reactive power that it needs to deliver? So that is what they will ask. That is what they will ask. So how will you find it out actually? Okay. But like in the question, this kind of question will come. They will not give you like this was just to explain you all this, but they will not give you this, right? This they will not give you. So how will I find this out? So we have to do the reverse engineering. So what is the overall reactive power that I need to send if my power factor is 0.61? So we know this formula. I told you we will use this formula, that is Q equals to P tan phi. So in the case 1, this is, let's say this is the case 1, this is the case 2, right? So in the case 1, what is the amount of reactive power that the supply sends? Q1, that is equals to active power is constant. VAR compensator cannot deliver any active power, right? It can only deliver reactive power. So Q1 is P into tan phi 1 and Q2 is P into tan phi 2. Okay. So what do I need to find out? I need to find out Q2, or how much additional the VAR compensator needs to send. So Q1 was the reactive power sent by the supply initially, and Q2 is the reactive power sent by the supply after the VAR compensator. So who is sending this additional reactive power? VAR compensator. So Q1 is the higher value, because initially the supply was sending more reactive power. Q1 will be higher. So Q1 minus Q2 will be the amount of reactive power that the VAR compensator needs to deliver to the load, so that my supply does not have to deliver this VAR. This VAR compensator delivers this VAR, so that the power factor improves, so that the magnitude of current improves. So that's how you derive the formula. In most cases, this chapter, right, they will start directly with this formula, but we took almost 30 minutes to come to this formula, because I don't want to teach formula. I want you to understand the concept. Remember, whatever we are discussing with respect to a lagging route. Okay, we are discussing with respect to a lagging load. I hope that part is clear. Okay, this is the actual formula that they will derive basically. So your reactive power sent by the VAR compensator QVAR, and they will tell you to remember this formula, but I am not telling you to remember this formula. Okay, understand it with basics. Tan phi 1 minus tan phi 2. Okay, so that is what my QVAR is equals to. I hope that is clear. Like this formula will be utilized everywhere. So now one more topic they will ask. Now how will I improve this? How will I send reactive power? What element delivers reactive power? What element delivers lagging reactive power? Capacitance. Capacitance delivers the lagging reactive power, right? Capacitors deliver lagging reactive power and inductors absorb lagging reactive power. Inductors deliver leading reactive power. Capacitor absorbs leading reactive power. Okay, I hope these points are clear. So I will write this again. If you don't understand, you have to watch the network theory. So these are the very important points that you must understand. Okay, point 1, inductor absorbs lagging reactive power. Okay, your capacitor absorbs leading reactive power. Okay, your now your inductor delivers leading reactive power. Inductor delivers leading reactive power and your capacitor delivers lagging reactive power. So capacitor can be actually utilized to deliver the lagging reactive power whatever the inductor demands. Okay, so these are the very important points. So leading reactive power, lagging reactive power, if it is absorbing, we say it to be Q greater than 0. That is how we define it. And if it is absorbing leading reactive power, we say Q is less than 0. Q is negative. If we say if we say it is delivering leading reactive power, which is same as absorbing lagging reactive power, we say Q is greater than 0. If it is delivering lagging reactive power, which is same as absorbing leading reactive power, we say Q is less than 0. Okay, so these are the few important points. Now of course what we will do, we will connect a capacitor here. Now we need to find out the value of the capacitance that will actually help us to deliver this much amount of reactive power. Okay, how will you find it out? So there are two connections. First one is if the capacitors are connected in star, right, then what is the overall power delivered by the capacitor? Power delivered by the capacitor, right? Power delivered by each capacitor per phase power. Okay, I'm talking about the per phase power delivered by each capacitor, or let's find out overall power. So per phase power, right? Q per phase, QC per phase. It will be what? Let's like if a per phase, I am talking about the per phase power, then I will find out the phase voltage, V phase, and the capacitance value. Let's say the reactance is XC. So with respect to voltage, what will be the reactive power? So here, right, I defined that my reactive power is equals to I square into X. So if it's a single element, reactive power can also be defined if it's a single element, right? Have I defined it here? Here, yeah. If it's a single element, your reactive power also can be defined as V square by Xc if it is the voltage across it, right? So if I have a load, let's say capacitive load here, right, and this reactance is Xc, then this is V. So your reactive power Q will be V square by Xc. If the voltage here is fixed, right? If the voltage it is connected in parallel, so it will be V square by Xc. So I can use this formula here. So here it will be V per phase square, V per phase square by Xc. This is the per phase power. Okay. Now this, right, what is the three phase power? Q three phase, QC three phase, because I have capacitors connected in all the three phases, it will be just 3 multiplied by it, right? V phase whole square divided by Xc. Now I know this value is equals to what? This is the overall reactive power demand, right? That the capacitor will deliver. That is how much it has to deliver. It has to deliver this much amount of reactive power, right? So I will equate with this. So you will get a formula for the Xc basically, or the C phase. This will be equals to, now what is your yeah, this is fine. Xc is omega. Yeah, this is fine. So what is your Xc actually? Your Xc is 1 by omega c, right? So it will be omega c into V phase whole square. C per phase into V per phase whole square. So this will be per phase whole square. Okay. So now we will find it out. What is the value? The value is yeah. So that is equals to my P tan phi 1 minus tan phi 2. Okay. So from here I can get my C phase equals to P tan phi 1 minus tan phi 2 divided by 3 V phase whole square into omega. So don't remember the formula as such, because just in the next page I will show you a different connection, and there the formula will actually change. So if like this was the connection, this was for a star connection. If it is delta connected, if my capacitors are delta connected, right, then basically what will happen is my V phase will become VL, because per phase voltage will now become VL. So just be careful here. So now here what will be the per phase capacitance? The per phase capacitance here will be, my phase voltage will now become the line voltage, because here, right, it is a balanced system, so line and phase voltage will be different because it was in star connected. Now it is delta connected. If it is delta connected, my phase voltage will now become line voltage, because what will be the power delivered by the capacitor, that is the voltage across it divided by the XC, right here. So now the voltage across it is V line, it is not V phase anymore, it is V line. So this will become V line by XC. So what will be the power, sorry, not the power, reactive power delivered by the capacitor? It will be XC per phase. It will be equals to, it will be equals to V VL whole square divided by XC, right? Because now the voltage across the capacitor is VL, it is not V phase anymore. So just be careful about this. It is VL. So now QC three phase will be 3 into VL whole square divided by XC. Okay, just be careful regarding this, because actually if they have given you the phase voltage, right, then you have to convert that into line voltage, because your capacitors are connected in delta. And if they have given you the line voltage, you have to convert in phase, because your capacitors are connected in star. So remember, if capacitors are connected in star, you must find the VC, that is V phase. You must find out the phase voltage. Okay, by default always in the question line voltage will be given. And if the capacitors are connected in delta, then your VC will become line voltage, and by default anyways in the question line voltage is given. And if nothing is mentioned about the connection of the capacitor, you will assume star, but most cases by default assume this, but in most cases they will mention that it is star connected. Okay, so this will be here, right? This will, the formula will be same, just instead of V phase it will become VL. This will be 3 VL whole square into omega. Okay, so I hope it is clear. Just be careful regarding the formula. I am not telling you to remember the formula, understand it conceptually, whatever is happening. Okay, so let's do few questions, and from this concept we will understand it even better. So here a 220 kilovolt transmission line supplies 10 megawatt load operating at power factor this. Okay, so I have a transmission line that is 220 kilovolt. Remember, whenever they are talking about transmission line and they have given you the voltage, this voltage is actually line voltage. Okay, so your V line is 220 kilovolt. Okay, then okay, then they're telling me determine the required per phase C phase capacitance C phase of the capacitor bank if, like, the what is the load power factor? Load power factor is 0.6 lagging, right? 0.6 lagging. Okay, and the load, right, demand, active power demand is 10 megawatt. 10 megawatt. Okay, Now what they are asking me that it is delta connected, the capacitor bank is delta connected. So in the formula that whatever we derive, I will not, like, I will go with basics only. Okay, it's not like I will not derive with basics. I will not try to remember the formula. Okay, but one thing is it is delta connected. If it is delta connected, then the reactive power delivered by the capacitor, right, will be overall reactive power, three phase reactive power delivered by the capacitor will be 3 into VL whole square divided by XC, that is omega C into, or I can write VL whole square divided by XC, because the capacitors are connected like this. And what is the per phase power? Per phase power will be voltage divided by the reactance. So it is VL whole square divided by the reactance. So that's why it is line voltage, and multiplied by 3 because this was only a single phase power. 3 phase will be multiplied by 3. That is the power delivered by the capacitor. Now what was the initial reactive power? Initial reactive power, right, Q1 is equals to P tan phi. So what is your initial power factor? So power factor they want me to improve from 0.6 to 0.9 lagging. Okay, 0.6 to 0.9 lagging. So what is the power factor angle phi here? So it will be, I think, 37.13. So 0.6 cos inverse 53. 13 degrees. Okay, that is what my power factor angle is. So it will be P tan phi, P tan phi 1. Okay, P is constant, it is 10 megawatt. So 10 mega into tan of 53.13, tan of 53.13, I think it will be 0.75 or something, right? Tan of this, yeah, sorry, 1.33. So it will be 13.33 MVAR. That is what my initial reactive power demand. On initially there is no capacitance connected, so this will totally be supplied by the supply, right? Now I have connected a VAR compensator, that is the capacitor bank. So capacitor bank will deliver some reactive power. So if the capacitor bank delivers some reactive power, so what is the overall reactive power sent by the supply? They have given me the power factor has been improved from 0.6 to 0.9. Which power factor? Of course your load power factor is constant. If you are connecting a fan, how can you change the power factor of your load? Load power factor is constant. They are meaning that by default you have to understand this, that they are telling you that the supply power factor has been improved. Okay, load power factor will always be constant no matter what. Your load reactive power demand will be constant, it will not change. So what they are meaning is your supply power factor has changed. So your load power factor cos phi L will always be constant. Your load power factor cos phi L will always be constant. We are improving the supply power factor. Okay, so this reactive power actually is the supply reactive power, right? Whatever is the reactive power sent by the supply. So in the case 1, what is the reactive power sent by the supply? Because active power, it does not matter, because active power supply and the load is constant, that will not vary. So that will be equals to tan of phi S1, and in the first case your load power factor and the sending and power factor are same, so that's why this was same as the load power factor. Now we have improved, so now our cos phi S has been improved to 0.9. So now what will be my tan phi S2? Okay, tan phi S2 will be 0.9 tan inverse, right? Or sorry, no, not cos inverse 0.9, that is 25.84, I guess. Okay, tan of this, so this will be equals to 0.5 484. So my reactive power, right, sent will be P into 10 5 is to, so this will be P is 10 megawatt, so this will be actually 4.84 MVAR. So my supply now has to send lesser amount of reactive power. So who is sending this additional reactive power? Capacitor. Okay, capacitor is sending this additional reactive power. So QC will be simply equals to QS1, what the overall reactive power, minus the QS2, which is sent by the supply. So additional reactive power will be sent by the capacitor, that is, this will be equals to plus 13.3333, this will be 8.49 MVAR is sent by the capacitor. So what will be the overall capacitance value, per phase capacitance value? It will be equals to so this value, right, is equals to what? This value is equals to 3 into VL whole square. VL is given to me, that is 220 kilovolt. So I will write in kilo only. So kilo whole square will become mega, divided by XC. So that is basically omega into, that is omega is 2 pi into 50, right? I hope it is 50 hertz. It is okay. They should have mentioned what is the frequency. They should have mentioned it actually. So yeah, they should mention transmission line frequency is 50 hertz. The assignment question also have to change. What is it? Here your frequency will be 50 hertz. Okay. So yeah, frequency is 50 hertz. So this will be C phase, right? Okay. So this will be omega 50 into C phase. So from here I will get my value of C phase. Let me just quickly calculate this. Divide by 3 into 220 whole square into 2 into pi into 50, this, right, into 10 raised to power 6. So it comes out to be 0.184 186 microfarad. Okay, that is what it comes out to be. So that is what my per phase capacitance. Now per phase capacitance is, I solved it very slow, right, very slow. Of course you can use the formula, right, what most guys will do, directly use the formula. What is the formula? C per phase will be your P into tan of phi 1 minus tan of phi 2 divided by 3, as it is delta connected, this will be VL square into omega. You can use the formula, no problem with that. You can always use the formula, right? But I try to solve with basics, but because even if you tend to forget the formula, still you can do it, right? So here, right, what you'll do, like if you want to directly solve with formula, your phi, you will find out your phi 1, what will be a phi 1? Cos inverse of 0.6, and your phi 2 will be cos inverse of 0.9. So this is how you will solve, right? First you will find out cos inverse of 0.8, 0.6, then you will do the tan of that. So that will be your tan phi 1. You will find out cos inverse of 0.9, because that will give you the angle. Then you will find out the tan of that. So that will be whatever is the tan angle, right? Then you will multiply that by power divided by 3 VL whole square into omega. Okay, so that is what your this value is, right? So yeah, that's how you solve this kind of question. So let's go through a bit of theory. So I hope now you understand why power factor is important. Power factor is a measure of how effectively electrical power can be converted into useful work, because it is basically that, it is literally the ratio of the active power by apparent power. So I want my supply to send as much as active power as possible. I don't want it to send other things, right, reactive power and all those things. I want reactive power to be delivered by some capacitor or something. Okay, I hope that is clear. So these are the advantage: reduce line current, lower electricity bills. Like if your load is low, if your load is very low power factor, right, your electricity supplier can charge penalty on you. Why it can charge penalty? They can tell you that due to your low power factor load, the current on the transmission line is very high, because let's say your load has a power factor of 0.2. Even if the power, right, is very small, 1 kilowatt or something, right, 1 kilowatt, but as the power factor is very low, the current, line current will be huge to only deliver this much amount of active power. So the electricity supplier will say to you that you are wasting so much, like so much of current is going out, that is causing huge losses on the line, so we will charge you penalty. So if you are able to improve your power factor, let's say you are a consumer and you connect a capacitor just in front of your meter, right, or in front of your load, then your electricity bill will actually come out to be lower, because if you go in your go and see your electricity bill, there will be a section of power factor. So higher the power factor of your load, the lower will be your cost, electricity bill basically. Okay, so that because your electricity suppliers will charge you less penalty. Then there will be enhanced system stability. A low power factor implies a higher proportion of reactive power, which can compromise voltage stability and power angle stability. So basically, uh, if the power factor is low, then the reactive power is much higher. Okay, so the stability actually takes a hit. Stability takes a hit when the like reactive power is much higher, then the voltage stability and power factor stability, sorry, power angle stability, both will take a hit. And obviously if your power factor is high, there will be better voltage regulation, because the current will be, magnitude of the current will be lower, so your drop, right, I into R, I into Z drop, this will be lower, right, so your voltage regulation will be improved. Okay, so yeah, these are the things basically that you need to keep in mind in case of a power factor. Okay, I hope that is clear. Now let's do few questions. Through this we will understand this even better, right? One more thing is that, remember this thing, that your capacitor can never deliver any, like if it's a ideal capacitor, it can never deliver any active power. So if I have a load connected, just let's see, if I have a load connected over here, let's say a purely resistive load of 1 ohm, right, and let's say I am connecting a voltage of 10 volts, right, let's assume for now it's a sinusoidal source only, it's a 10 volt, 10 sine omega t, and how much will be the power delivered here in this case? What will be the current? What will be the RMS value of the current? RMS value of the current will be 10 divided by root 2. So what will be the power consumed here? It will be I square, I RMS square into R, right? This is the RMS value, don't forget, this is the RMS value. So it will be I square into R into R. 50 watt. Okay, 50 watt. So power consumed is 50 watt. Now if I connect a capacitor, will it deliver any active power? Let's say its reactance is minus J. Will it deliver any reactive power? No, it will never deliver any reactive power. Why it will not deliver any, sorry, will it deliver any active power? It will never participate in the active power deliver or absorb, right? It will not never participate in that deal. Why? What is the current through it? What will be the current? If the voltage, let's assume that voltage, I assume VRMS angle 0 degree, right? What will be the current? The current will be IC will be 10 root 2 angle 0 divided by minus of J, the reactance basically, this will be plus J. So IC comes out to be 10 root 2 plus 90, right? So what is the active power delivered by the capacitor? It is VC into IC into cos of phi, right? it will be Vc is 10 by root 2 Vrms into Ic is 10 by root 2 into cos of angle between voltage and current, that is cos of 90, which is 0, right? So it will never participate in the active power. That's why your active power is always constant, right? If you connect a reactive power device, like almost all cases, sometimes it is not constant, we'll see those examples as well. But when you were connecting any capacitor bank, or we are connecting any synchronous motor working at no load, in those kind of cases your active power demand will be constant. Okay, active power demand will be constant. For capacitive compensation, capacitive compensation for different kind of compensation, we will see this will change. Actually, the active power will not be constant there anymore, but in this case it will be constant. Okay, I hope that is clear. Now let's solve this question. A shunt reactor of 100 MVAR is operated at 98% of its rated voltage and 96% of its rated frequency. Okay, the reactive power absorbed by the reactor will be, it's a reactor, so they are telling it's just an inductor, right? Inductor, shunt inductor, right? So what will be the reactive power absorbed? So that whatever QC we derived here, right, it is the reactive power delivered. How? So I can prove it to you. So what is the power factor angle over here? Phi. Phi is theta v minus theta I. Theta v minus theta I. Right? Theta v minus theta I. So that will be equals to theta v is what? 0 degree. Theta I is what? Plus 90, right? So it comes out to be minus 90. So what is your reactive power? QC, it will be Vc into Ic into sine of phi. So Vc, that is 10 root 2 into Ic, that is 10 root 2 into sine of phi, that is sine of minus 90. Your power factor angle is negative, right? So it comes out to be minus 50 VAR. It comes out to be minus 50 VAR, right? Minus. Haven't I told you this, right? If it is negative, if my reactive power is negative, that means what? That basically means that it is absorbing leading reactive power or it is delivering leading reactive power. All this have been taught in basics, right? So that is what negative reactive power means, and that's how I can prove it to you that capacitor will deliver negative reactive power. Sorry, it will deliver leading reactive power. So it will deliver lagging reactive power and absorb leading reactive power. Okay, here if it is reactor, that means this is absorbing lagging reactive power. Okay, it is not delivering, it is absorbing lagging reactive power. Now let's come back to the question. I have an inductor connected and they are telling me that across the shunt inductor I have some voltage, right, V phase, and I will have the this inductor value, that will be what? That will be omega into L, right? So how is the rating of this inductor calculated? It is simply QL, right? It is inductor, not a capacitor. If it was a capacitor, they would have told you. Reactor basically means it is an inductor. So QL will be V phase whole square divided by XL, that is omega L. Okay, that is omega L, right? So now they are telling us that what is omega? Omega is basically 2 pi f, 2 pi f. So now this rating is actually 100 MVAR. Now they are telling me that I am reducing my voltage to 98% of its rated value. So my V phase, new V phase dash is becoming 0.98 of the previous value, and the new frequency is 96% of the previous value. So f dash is 96% of the previous value. Okay. So from here we can actually find out what is my QL. Right, what will be the new QL dash? It will be VPH dash whole square divided by 2 pi f, so L is also there, right, 2 pi f dash into L. So this, right, will be equals to 0.98 whole square into VPH whole square divided by 0.96 into 2 pi FL. Okay, so this will be equals to QL dash. So yeah, so now what will be the value? Value will be 0.98 whole square divided by 0.96, and this value is already known to me, right? This value is already known. What is this value? 100 MVAR. So it will be basically 1.00044167 into 100 MVAR. What are they asking? They are asking what changes will be there, right? Very minute changes actually. There will be very minute changes into 100. It comes out to be very low actually. Yeah, 100.04 MVAR. So the new MVAR of the inductor comes out to be 100.04, that is present in option D. Let's solve the next question. So they have asked a question like the power factor, right? So they're asking what is the like which P1 is positive, negative, which power is positive, negative. So one thing we know, basic, right? What basic we know? We know power. If it's an inductive link, power always flows from higher angle. Just give me 1 second. Power always flows from higher angle to lower angle. Power always flows from higher angle to lower angle. For inductive link, okay, if it's an inductive link, power will flow from higher angle to lower angle. So what are they telling? That in the figure V1 is cos omega t, so this is angle, so I'll take this, right, or maybe on this and only I can do, this is angle V, angle of 0 degree, okay. V2 is pi by 18. Pi by 18 is what? Pi by 18 is 10 degree, right? V angle 10 degree, and V3 is pi by 36, so it will be V angle 5 degrees, okay. Now the circuit is in sinusoidal steady state and R is much less than omega L. So basically what they're telling, it is almost a pure inductive link, right? It is almost a pure inductive link. Which of the following P1, P2, P3 are all average power outputs? Which one of the following statements is true? All power will be 0? No. Which will, can you tell me which one will deliver the power? P2 will deliver the power. P2 is at the higher angle, so P2 will deliver both here and here. Now if P2 is delivering both here and here, right, so P3 has to be negative, P1 also has to be negative, because this has the highest angle, so it is delivering, right? There is no other possibility, power will only come out from here. So if power is coming out, right, then these two will receive the power. So as P2 has higher voltage angle. This right has been covered in basics. Higher voltage angle, your P2 will P2 will deliver the power. So P2 will deliver, and P1 and P3 has to absorb because P2 is connected at the junction. If it was connected at some other place, then also it would have been it has to deliver only. Let's say here, right here, this was P2, this was the higher angle, so this is delivering the power. If this is delivering, this one has to receive, this one has to receive. So anyways, both of them don't have any option, right? P1 P2 has to absorb power. There are no other options. Both of them has to absorb power. So P1 P3 will be negative. They are not delivering. They are telling that it is delivering. No, it is not delivering. These are absorbing, right? And this is delivering. So P2 will be positive, P2 will be positive, P3 will be negative, P1 will be negative. Option C will be correct here, right? If I see about the options as well, P2 is positive, P3 is positive. No, P3 cannot be positive. P2 is negative, P2 cannot be negative, P2 cannot be negative, P2 cannot be negative. That's it. Okay, P3 has to be positive. P1 and P3 they are telling positive. No, not possible. Okay, so I hope that is clear. Let's solve the next question. So we have a synchronous motor consuming 50 kilowatt is connected in parallel with a 200 kilowatt load operating at a power factor of 0.8 lagging. If the overall power factor of the combined system is known, determine the power factor at which the motor is operating. So here, right, actually the overall power factor of the system here, right, this should have been 0.9. My bad. This should have been actually 0.9. This will be 0.9. Known, that is 0.9 lagging. Missed this. Okay, so it will be 0.9 lagging. Missed that part. So this I have to copy there, right? Here, yes. Now if it is 0.9 lagging overall power factor of the system, then determine the power factor at which the motor is operating, right? So I have a load connected. So to solve all these questions, go by basics. So my load is connected, which is taking 200 kilowatt at 0.8 power factor. Now I suddenly connect a motor, right? Motor obviously will be connected across the supply. So I have a motor connected, right? Remember, this is a motor, this is not a generator, it is a motor. So motor is taking 50 kilowatt of active power. I don't know what is the reactive power, but the power factor of the overall system is 0.9. So overall system has a power factor, that is the sending end power factor is 0.9 lagging, right? What does it mean basically? We can use this formula. What is the sending end reactive power? It will be sending end active power into tan of phi s. So what will be tan of phi s? So tan of phi s will be simply sending end. What is the sending end power? 50 kilowatt in the motor, 200 kilowatt in the load. So 200 plus 50 into tan of cos inverse of phi s. Okay, 250 tan of cos inverse of 0.9. So this will be 250. So what is cos inverse of 0.9? 25.84. Tan of this is 0.84 into 250. So it comes out to be 121.08 kVAR. kVAR. Okay. So yeah, that is the reactive power basically. Now what can we calculate? So this is the sending and reactive power. Now motor will also absorb some reactive power, correct? Because motor is, like we're assuming motor is operating in lagging, but we can be wrong, right? If my assumption is wrong, then the answer will come out to be negative. And your obviously load is also operating in lagging, right? 0.8 lagging. Load also will absorb some lagging reactive power. So what is QL? QL will be PL tan phi L. So PL is 200, tan of phi L, that is tan of cos inverse of 0.8. So 0.8 cos inverse in tan of this into 200. So it is 150 kVAR. Okay. So actually we are kind of wrong. We are telling that our supply is delivering 121.08 kVAR, right? And but my load is absorbing 150 kVAR, lagging kVAR. That means the synchronous motor will actually deliver some kVAR. It is not operating in lagging power factor, it is operating in leading. So this will be QM will go outside. So I understood that QM will be negative, will come out to be negative. So automatically I change the sign. Assumption is QM is operating in that is my motor is operating in leading power factor. That is what I can conclude, right? Otherwise the equations will not match up, right? So what will be the power factor of the, what will be the reactive power delivered by the motor? It will be whatever is the reactive power demand. So basically what is the overall reactive power delivered? Overall reactive power delivered will be here by the supply QS plus QM will be equals to the total reactive power absorbed, that is QL. So this will be the overall reactive power exchange. QL plus QM will be equals to QL, right? So here what we can say, what will be QM from here? QM will be QL minus QS. So automatically it will come out to be positive because I have assumed my sign properly. If I would not have assumed my sign properly, simply your QM will come out to be negative. That's it. Simply your like motor reactive power will come out to be negative. But as I have assumed my sign properly, your motor reactive power will come out to be positive, and this reactive power is leading reactive power. This reactive power will be leading reactive power, okay? Because I have already changed my sign of the motor automatically. Okay, so this will be QL will be 150, QL is 150 minus QM, that QS, that is 121.08, right? So minus 121.08, so it comes out to be 28.92 kVAR. Okay, now what will be the power factor of the motor? So I know this formula. QM will be again the same formula, PM into tan phi m. Tan phi m will be equals to what? QM by PM. QM is 28.92 and PM is how much? PM is 50 kilowatt. 50. So this will be this divided by 50. So tan inverse of this 30 degree, right? So your phi m comes out to be 30 degree, and cos of this will come out to be 0.866. So your cos of phi m will be 0.866, and remember it is leading. because already I have taken the sign that the motor is delivering reactive power. If the motor is delivering reactive power, it will be leading. You might have a question, sir, here QM is positive, here QM is positive, right? You might have a question, sir, QM is positive, it should be lagging, right? Because here I told you that if your reactive power is positive, it should be lagging. What went wrong? I automatically change the sign, right? Because synchronous motor is a load, so it should actually originally, it should, the direction should be like this, QM should be like this, right? It is a load, correct? But I have already changed the direction of the reactive power, so I have already assumed it to be leading because it is delivering lagging reactive power. So I have already taken the sign. If I wouldn't have taken the sign, if the reactive power would have been downward, simply your QM will come out to negative. From that also you will understand that it is not absorbing lagging reactive power, it is delivering lagging reactive power, or we can say it is absorbing leading reactive power. Okay, I hope that part is clear. Let's now move on to the next question. So a complex power consumed by a constant voltage load is given by P1 Q1. Okay, so complex power consumed by a constant voltage load, so voltage is constant there. Okay, voltage is constant, where P1, the range of P1 is this, range of Q1 is this. A compensating shunt capacitor is chosen such that your magnitude of Q is between 0.25 kVAr, where Q is the net reactive power consumed by the capacitor load combination. So basically if the voltage is constant, so basically we are connecting the load across the supply, that is what they are meaning. Okay, and then I am connecting a capacitor. Basically if I am connecting a capacitor and this is my load, now the combination, they are telling me the combination is taking magnitude of reactive power after the combination is between 0, like magnitude will be 0.25 kVAr, that is either it will receive 0.25 kVAr or deliver 0.25 kVAr, where Q is the net reactive power consumed by the capacitor load combination. Okay, the reactive power supplied by the capacitor will be, so how much is the reactive power supplied by the capacitor, that is what they are asking. Okay, so what is the reactive power range of the load? So reactive power range of the load, right, it is plus jq1, so it will always absorb the reactive power. This is lying between 0.5 kVAr to 1 kVAr. Okay, right. So now what we can do is, now we are telling that overall reactive power sent from here is 0.25, like magnitude of 0.25, right? So capacitor, what will be the reactive power supplied in kVAr by the capacitor is, what will be the reactive power supplied by the capacitor? So here, right, if I choose Q1 to be maximum, let's say it is taking 1 kVAr, so capacitor will deliver some constant reactive power only, right? Because voltage is fixed, load might be varying, but voltage here is fixed. So if voltage here is fixed, capacitor will deliver some QC reactive power, correct? Capacitor will deliver some QC reactive power. So Q, overall reactive power, plus reactive power delivered by the sending end, by the supply, plus QC will be equals to the load reactive power, that is Q1. Okay, now QC is fixed, this value is fixed, right? Because they are asking me some exact value of capacitor reactive power, so this value is fixed. So when this will be maximum, then QS will be maximum. When Q1 will be maximum, QS will be maximum. So what is the maximum value of Q1? Maximum value of Q1 is 1 kVAr. Okay, so maximum value of QR is 1 kVAr. QC is this value, and what is the maximum value of QS? It is 0.25 kVAR. It cannot send beyond this capacitor value. It has to be 0.25 kVAR, right? Maximum value is plus 0.25 kVAR. Maximum reactive power, maximum lagging reactive power that this supply can deliver is plus 0.25 kVAR. So this will be plus 0.25 kVAR. Okay. So this will be QC will be equal to 0.75 kVAR. Okay. Now what will be the minimum value here? Minimum value will be 0.5 kVAR. When this is minimum, right, then like we can cross verify whether this QC is correct or not. When this is minimum, my QS also should be minimum, right? So let's cross verify. So QS, I don't know what is the minimum value. Let me write QS minimum plus QC, that is 0.75 kVAR, equals to Q1 minimum. What is the minimum value of my load reactive power? 0.5 kVAR. So this will be 0.5 kVAR. Okay. So your QS will be QS minimum will be minus 0.25. Is it true? Is it correct? That is it what the minimum value of QS is? Yes, because magnitude of QS is 0.25. What does magnitude mean basically? Magnitude means it can be minus 0.25 magnitude is also 0.25 only, right? So basically this means Q will lie between 0.25 to minus 0.25. So from here I can directly say that the minimum value of Q is minus 0.25, which I can here cross verify as well. It comes out to be minus 0.25. So your QC will be 0.25 basically. QC will be reactive power sent delivered by the supply will be 0.275 kVAR. So not 25, 0.75 kVAR. So that is what my reactive power will be. Okay, this is my answer. Okay. Now let's solve this question. So yeah, I think we will just solve all these questions. We will end this lecture here only. So remaining things we will solve in the next lecture, like remaining topics we will cover in the next lecture. Today will be till this question only. Okay. So a 400 volt 50 hertz 3-phase balance source supplies a power to a star connected load rated at 12 under root 3 kVA, power factor of 0.8. So it's a star connected load, correct, and it is operating at a power factor of 0.8 lagging, and what is the kVA rating? kVA rating S is 12 root 3. Okay, it's a balanced load. Determine the kVA rating of the delta connected capacitor bank required to improve the power factor to unity. So what I have to improve the power factor to unity basically of what? Of the supply. They will not tell you this. They are telling you to improve the power factor to unity of the supply, right? They will not explain you this, right? You have to understand. So how can the power factor be, like, how can the power factor be unity? When is my power factor unity? When my phi is 0 degree. That means your sin phi will be 0. That means your reactive power sent from the sending end, from the supply, will be 0. So whatever is the reactive power demand, that will be delivered totally by the capacitor bank, right? Delta connected capacitor bank. So what is the reactive power demand? What is the reactive power demand? QL. So reactive power demand is basically from here I can find out it is S sine phi L, right, which will be 12 root 3 phi L is 0.8. So cos phi L is 0.8. So your sin phi L will be 0.6. So this will be into 0.6, right? This will be equals to point into 0.6. So this will be equals to 12 into 0.6. So 7.2 under root 3 volt ampere kVAR will be delivered by the capacitor. So what is this? What is the capacitor formula? It is V, remember it is delta connected, so it will be V line square, right? Per phase power will be, per phase reactive power will be V line square upon XC. It is per phase, so I have to multiply 3 because it is a 3-phase system. So from here I can directly write that my C phase will be equals to 7.2 under root 3 into 10 cube, because it is kVAR, divided by 3 into VL whole square, that is 400, right? 400. If a voltage is mentioned, if it is a 3-phase system, by default you will assume it to be line voltage. 400 volt whole square into omega. Omega is 2 into pi into F. So this will be okay, 3 into 400 whole square into 2 into pi into 50 into 10 cube into root 3 into 7.2, sorry, 0.8 into 7.2. So it comes out to be 8. Your reactive power comes out to be your capacitance value comes out to be 8.27, sorry, 82.7 microfarad. Okay, this is your per phase capacitance value. So I will again write calculate what is the, I will just quickly recalculate this value, right, to check everything is correct. So this will be 7.2 into under root of 3 into 10 cube divided by 3 into 400 whole square into 2 into pi into 50, yeah, 8.27 82.7 microfarad. This will be the answer of this particular question. Okay, pretty straightforward and simple. So in the next lecture we will discuss what are the different methods of power factor improvement, and also we will solve few more questions. Okay, let me end this. Yeah, so that's it basically for today's lecture. Hi everyone and welcome back to PrepFusion. So today we will start with the lecture 30 of power system. So today we will discuss few voltage control techniques, how to control the voltage, because that is also important, and then of course we will discuss few more methods to improve the power factor, voltage control methods to control voltage and improve power factor. Okay, so why is voltage control like important? First of all, our voltage, right, if my load current increases, how will load current increase? By reduction in cos phi, that is the power factor, reduction in the power factor, right? If my power factor reduces, my cos phi will reduce, so my load current will increase. Okay, so if my load current increases, then what will happen? Then I know the voltage Vt, what is Vt? Vt equals to EF angle delta minus I into R plus Jx. Basically there will be some voltage drop. So if the load current increases, your magnitude of the voltage will go down, and if voltage go down, there are multiple problems, right? It will affect the equipment operation. So if your equipment is rated to operate at 220 volt, okay, to 20 volt, then if the voltage reduces to, let's say, 200 volt, right, then that is a problem to us, correct? That is a problem to us, right? If the voltage reduces to 200 volt, that is a problem, right? So we don't want that, and of course it will lead to inefficient power delivery. If voltage is reducing, that means basically your current is increased. That basically means that there will be more line losses, and there will be problems during peak hours, right? Peak hours meaning when there is high load demand, the voltage will drop down suddenly, and if it drops down, right, if this voltage drops down, there are multiple loads connected, that will cause a fluctuation, instability of the system, right? So that's why we limit between plus minus 6%. So how can I basically improve the voltage? How can I improve it? So we know that we have derived this already, that if in a transmission line, if the resistance is much smaller than the inductance, then the power at the receiving end formula comes out to be this, and the reactive power at the receiving end comes out to be this formula, correct? Now what we have told you, generally we operate near delta equals to delta less than 30 generally, right? Delta operating or operating power angle is less than 30. Why? This has been taught to you in machines for better stability of the machines. If my delta is very high, right, it can go near the instability region. Maximum delta value can be 90, right? So we want to be as much away from 90 as possible. So we want to be near to 90, sorry, we want to be near to 30 degrees. So we want to be near about 30 degrees. So my delta operating must be less than 30 degrees. My delta operating must be less than 30 degrees. Okay. That is the thing over here. Delta operating must be less than 30 degrees. So what I can say is that if it is less than 30 degrees, right, your cos delta roughly will be roughly 1. Okay. So from this, right, I can write QR roughly will be magnitude of Vs, magnitude of VR divided by X. Into cos delta into 1 almost minus magnitude of VR square by X. Okay. So what I can say is, like this we have learned previously as well, that my reactive power, right, is equals to, if I take the VR common, is proportional to the voltage difference. It is basically delta V is what? Delta magnitude of delta V is basically magnitude of Vs minus magnitude of VR, which is basically proportional to the voltage regulation, right? That is what I want to control. I want my Vs and VR to be as near to each other, because my fluctuation must be between plus minus 6%. That basically means if my Vs is 100 volts, my VR minimum can be 94, maximum can be 106. So here if it is 100 volts, my VR minimum can be 94 or 106. That is the maximum and minimum values. So I want this difference to be as less as possible, right, between 6 plus minus 6%. So that is this difference, this delta V. I want to control this delta V. the receiving end voltage we assume it to be constant. We want to keep the receiving end voltage to be constant. So if I want to control my delta V, I have to control my reactive power at the receiving end. If I reduce my reactive power at the receiving end, the delta V will reduce. So that's why, that is also another reason why we connect a like compensator, reactive compensator at the load end to reduce the receiving end power, because then what is the receiving end power? Whatever the supply is sending, right? So of course the load will take some reactive power, that is fixed, but if I connect a VAR compensator, that will deliver this power. So QR, the receiving and reactive power here, right, will reduce, because whatever was the required reactive power by the load, that already has been delivered by the static VAR compensator. So this QR will go down, so this end voltage will be stable. Okay, now few conclusions. What we can see, my QR is proportional to delta V. So if my, not magnitude of delta V, sorry, just delta V, right, just delta V, not magnitude, sorry, it is a number, it is not a positive number, it can be negative or positive. When it can be negative or positive, it can be negative and positive. If my, so if my magnitude of Vs is greater than magnitude of Vr, then my QR is positive. That basically means what? When is reactive power positive? When the load is inductive load. Okay, when load is inductive, then only the reactive power is receiving and reactive power is positive, right? And when my Vs will be less than Vr, then my reactive power is negative. Okay, then my load will be capacitive. Okay, then my load will be capacitive. So these are the things that you need to keep in mind. Yeah, I hope it is clear. Now we will basically control our receiving and reactive power, right? We want to control our receiving and reactive power. So yeah, that were the derivations. Now in this, right, we also derived the sending and reactive power. What is the sending and reactive power? What was the sending and reactive power? Do you remember? The power will be same, but sending and reactive power will be actually different, right? Sending and reactive power will be different. So remember, the receiving end side is the load side. Receiving end side is load. So in the load side, if the reactive power is positive, that means basically it is absorbing inductive reactive power, and in the load side, if the reactive power is negative, that means it is delivering inductive reactive power. Okay, in the sending side it will be just the opposite, because in the sending side, source is the supplier, there is no load connected, it is supplier, it is supplying something. Okay, then things will be different there. Okay, so here if I derive the sending and reactive power, which we already have derived previously as well, right, again I will derive it. What will be the sending and apparent power? Sending and apparent power is Vs into Is conjugate. So which will be equals to Vs, magnitude of Vs angle delta into Is conjugate. What is Is? Is is simply Vs angle delta minus Vr angle 0 divided by Jx. So this will be minus of J Vs angle delta minus VR angle 0 degree whole conjugate. So whole conjugate I will do it here itself. So this, if I do the conjugate of this, right, so this will become plus J into Vs magnitude of Vs minus delta minus magnitude of VR, basically angle 0. So this will become Vs whole square angle 90 plus delta, sorry, minus delta, and this will be minus VSVR minus VSVR minus VSVR, just give me 1 second, minus VSVR angle of 90. Okay, delta should, sorry, this is my plus delta minus delta, this will be actually 0 and this will be 90. This will become 90 plus delta. Yes. So from here, right, what will be the active power and the reactive power? So active power will be cos of this, right? So magnitude of, so this, if I do the cos, okay, I forgot to divide by x. Divide by x is also there. Don't forget the x. Okay, x is very important, right? X is very important. So this will be divided by x. So active power, right? This will be cos. I will take the cos over the whole equation. Cos of 90 is 0. This will go away. It will become minus cos of VSVR by x cos of 90 plus delta. So my sine, if my cos delta is here, right, and my sine delta always lags here, sine delta. So cos 90 plus delta will be where? Cos 90 plus delta will be somewhere here, which is basically minus of sine delta, right? So I will replace this cos 90 plus delta with minus of sine delta. So this will be minus of sine delta. Automatically this will get converted into VR by x sine of delta. Now what does this mean actually? What does this mean? So in both the cases, right, if PS is positive, that is if delta is greater than 0, that means your PS is positive. That means my, here is, if the power is positive, that means it is delivering active power. Here if my PS was or PR receiving power, right, PR was positive, that means here also the delta is positive, right? What does it mean here? PR positive mean, that means it is absorbing active power, because receiving end side is the load side. Receiving end side is the load, so it is supposed to absorb. So if things come out to be positive, then whatever we have supposed, that is following. Okay, so PR positive meaning it is absorbing active power. Whatever we have supposed, it is actually doing that, right? And here PS positive meaning it is not absorbing, because my supply side is what? Sending end side. Sending end is not, it is not acting as a load, it is acting as a supply, right? Source. It is not load, it is source. So if it is acting as a source, then what will happen? If it is acting as a source, then, right, then if PS is coming out, like what is source supposed to do? Source is supposed to deliver the power, not absorb. So if PS is coming out to be positive, that means it is delivering active power. Okay, same thing we can derive for QS as well. So if PS would have came out to be negative, that means it would have absorbed, because it is not what it is supposed to do, right? If something is negative, that means it is opposite of what it is supposed to do, that means it is absorbing the active power. Now what about qs? Qs will be sending and reactive power will be, if I take the sign of this whole equation, that will be magnitude of Vs whole square by x minus, this also will be divided by x, right? Minus this will be magnitude of V sphere by sine of 90 plus delta. Okay, 90 plus delta, that is what my sending and reactive power is equals to. Okay, so what is sine 90 plus delta? So sine 90 plus delta, right, will be simply cos delta. Sine 90 plus delta will be simply cos delta. I am adding 90, so all these I have taught in phases. So this will be cos delta, so this will be equals to magnitude of Vs whole square by x minus magnitude of Vs Vr by x into cos of delta. So it is just coming out to be positive, right? If my delta, if my cos, like here, right, if I assume my delta to be very low value, although they are not exactly same, right? You're sending and reactive power, the value, the equation and this, right, are two different things, because here there was Vr square, here I have Vs square, both are different. Okay, just be careful. Whichever side you're calculating the reactive power, the voltage will be squared, other term will be Vs Vr by x. Okay, so here this will be basically qs. Qs will be equals to magnitude of Vs whole square divided by x, right? So now, like, what we can conclude, right? Again, right, assumption is delta will be very near less than 30, so cos delta will be almost approximately equals to 1. So here, right, my qs approximately, if I take common Vs, magnitude of Vs, it will be magnitude of Vs by x. Here, right, I forgot to divide by x as well, huh? No, x is there, Vs by x, so this will be magnitude of Vs minus magnitude of Vr, so this will be actually equals to magnitude of Vs by x divided by x into delta into V. Okay, so again here, right, if my Vs is greater than Vr, then my qs is positive. Okay, Vs is greater than Vr, then my qs is positive. What does positive mean here? It means it is delivering lagging reactive power. Okay, here if my qr was positive, load is inductive, that means it is absorbing. Load is supposed to absorb, supply is supposed to deliver. Here it is absorbing. Remember, all these things will be helpful either in power system or in some other place, trust me, but this will be helpful. Absorbing lagging reactive power. So that's the difference between a source and a load. Reactive power. Okay, so by default we assume that our convention is either source will deliver the lagging reactive power if it comes out to be positive, or load will absorb the inductive reactive power, lagging reactive power, if it comes out to be positive. So these are the few formulas that you must know. Okay, here also I think so basically with the help of synchronous condensers we can actually improve our power factor or control the voltage, correct? Because I hope you remember, right, overexcited, underexcited, right? By increasing the excitation our synchronous generator behaves as a capacitor. So I have taught this in electrical machines, so that's why synchronous machines is a very important chapter. So I hope I am expecting that you have studied the excitation of synchronous machine. I've already taught that very well. What does my synchronous machine behave when it is overexcited? When it is overexcited, my synchronous generator will deliver lagging reactive power. It does not matter whether it is synchronous generator or motor. So it does not matter. So I will write here, if, very important point, right, very important point, if my synchronous machine, generator or motor, okay, if anywhere they say that it is overexcited, is over excited, then it will always deliver lagging reactive power. Okay, very important point. It does not matter whether it is a motor or generator. This I have taught, right? If it was a so this thing you have to understand, that if it's a synchronous machine and it it is overexcited, so it will always deliver lagging reactive power no matter what. Okay, and the same thing I can say, if it is underexcited, it will absorb lagging reactive power. Okay, so if your synchronous machine, generator or motor is underexcited, okay, then it will always absorb lagging reactive power. So it will take the reactive power from the supply. It will not be able to deliver it. It will take it from the supply. Okay, I hope that is clear, right? So here few things are there, few terms are there. So source and sink of reactive power. So overexcited synchronous machine, right, supplies reactive power, so it acts as a source. Okay, it acts as a source of reactive power. So overexcited synchronous machine will act as a source of reactive power, and underexcited synchronous machine will act as a sink. Sink means where it is coming in, current is coming in, so it is acting as a sink of reactive power. Okay, I hope that is clear. Okay, so hence your overexcited synchronous machine will act as a source of reactive power, and underexcited synchronous machine will act as a sink of reactive power. So examples are, at night when industrial load is low, basically industries are low, right, then the reactive power demand is actually reduced. When industries turn on, like your whatever is your machine industry, right, tannery industry, any metal industry, construction industry, what does construction operate? What machines do construction operate in? Mainly they use motors. And what are motors? Motors are mainly induction motors, and induction motor is a lagging load. Okay, induction motor is a lagging load. So if induction motor is a lagging load, it will always act as a sink of reactive power. So during daytime, peak hours, normal time, right, when industries are open, then the reactive power demand will be higher, so your voltage delta V will be higher. So we have to manage that. At night, right, when industrial load is less, the reactive power demand will be reduced. So uh, what will happen if, like, we will connect the overexcited synchronous generator during day. So overexcited synchronous generator will be connected during day to meet the reactive power demand of the industries, right? And then if we keep that overexcited synchronous generator throughout the whole 24 hours, there is a problem, because at night industries will turn off, so the reactive power demand will go down, but still your overexcited synchronous motors or generators, whatever it may be, still they will deliver reactive power. Now you might say, sir, then what is the difference between overexcited synchronous motor and generator? The difference is a motor will absorb active power, a generator will deliver active power. Okay, I have not discussed about active power, so I will not say it over again. So I hope you are able to understand. So the difference between a motor and generator is very simple, right? It will always, motor will always absorb active power, generator will always deliver active power. Now sometimes what happens is, we say the motor is operating at no load. If it is operating at no load, then it will absorb zero active power only, either there will be transfer of reactive power. Okay, so a motor is very simple, right? I hope this I don't need to explain that a motor, difference between a motor and a generator. A motor absorbs active power, a generator delivers active power. Okay, we have not discussed about active power till now, right? Okay, so that is the problem basically. So we cannot keep the overexcited generator continue to supply the reactive power, because then the voltage will rise. Because if I am over supplying the reactive power, right, so my receiving end reactive power will go negative, because I have supplied more reactive power. Receiving end reactive power will go negative, because it will behave as a capacitive load, because I am delivering lagging reactive power, right? So that's why it will behave as a negative. So if it behaves as negative, that means your receiving end voltage will go above your sending end voltage. That's also we don't want, right? That is also, like, that thing also we don't want. Why? Because my machine is rated at 100 volt. If the voltage is 110 volt, right, the machine can get damaged. So that's why we don't want that condition as well. So uh, what we do is, to stabilize, sometimes the reactive power need to be absorbed. So sometimes we connect under excited synchronous machines to absorb that extra reactive power. And of course in daytime, when there is high VAR demand, we will obviously connect over excited synchronous machines. During night we will connect under excited synchronous machines. During day we will connect over excited synchronous machines. Okay, now transmission line, like this is how my synchronous motor behaves, or they are also sometimes called as synchronous condensers, because we are actually not using the synchronous machines as a generator or as a motor. We are actually using just to control the reactive power. So synchronous condensers sometimes are called as synchronous machines operating at no load. That means your active power is zero. Synchronous machines operating at no load. So yeah, now how does my transmission lines behave, right? Will my transmission line behave as a like lagging load, or will it behave as a leading load? Okay, so we know under lightly loaded condition in no load, if I model my transmission line, this we have already studied, it behaves as a capacitive load because your capacitance is dominating and huge charging current flows, and that effect is known as Ferrante effect. So during no load condition or lightly loaded condition, it behaves as a supplier of VR, so it behaves as a source of reactive power. And during heavy load, it will behave as a it will behave as a sink, because this drop will be dominating, so your inductive, it will consume more inductive reactive power. IC will be very less compared to the line current, so your inductive reactive power will be much higher. Okay, so at high heavy load it behaves as inductive, at light loads it behaves as capacitive. Okay, I hope that is clear. Why does it behave as inductive? Because in heavy load, right, what we do, we connect machines like induction motor, right? So that's why from the supplying end we see it as a sink of reactive power. Now one more thing is there regarding underground cables. So this, right, I will derive our underground cables, don't worry. But for now you just understand this. In underground cables the conductors are very near to each other. Okay, and we have derived in underground cables the conductors are very near to each other because you have very less amount of space. In overhead lines you have so much space, right, you can see the space, but in underground cables you have very less amount of space. Okay, so your conductors are very near to each other. So if conductors are very near to each other, I know the formula for inductance. It is ln 2 into 10 raised to power minus 7 ln of GMD upon GMR, and GMD is basically dependent on the distance between the conductors. So distance is low, so your GMD will be low, so your inductance will be low. Inductance will be on the lower side. What about capacitance? So capacitance, if you remember, it was 2 pi epsilon naught upon ln GMD upon GMR. Okay, GMD upon GMR. So again your GMD is on the lower side, so this will be on the lower side, so your capacitance actually will increase. So your C is higher, your L is lower. So your underground cable actually mostly behaves as a VAR generator or a source of reactive power. So your underground cables will behave as a source of reactive power, that is written over here. So capacitance per unit length will be higher, so it behaves mostly as capacitive, right? So it behaves mostly as a reactive power generator. Okay, especially under light load, anyways it will behave as a reactive power generator. But for heavy loads as well, like not for very heavy loads, medium loads as well, it will behave as a VAR generator. Overhead lines, we have enough space, right, between the conductors because there is air, so the distance is higher. Here the distance is much lower because the space is lower. Your underground cable, right, you don't have much space. So that is one thing to remember and understand. Okay, so I hope that is clear. Now we can derive as well how does my overexcited synchronous motor at no load behaves as a capacitor. I can derive that as well. I can derive that. So if I have a voltage here at the sending end, that is my let's say that is my sending end voltage, right? Vt terminal voltage, Vt angle 0 degree, and then I have the synchronous motor connected with its synchronous reactance, let's say X, and here I have the source, that is EF angle delta. Okay, EF angle delta, and delta is negative, then only the power will flow from source to load. Okay, so delta has to be negative. Delta has to be negative, that we already know. Delta has to be negative. So what is the formula? What is the formula? We have two voltages, right? What is the active power formula? Active power input to the motor. What is the receiving end reactive power? That is at this terminal. It will be EF Vt into sine delta. Okay, but delta is here. Okay, delta is here, so it will be EF Vt by X into sine of minus delta, sine of minus delta. Okay, so this will be minus EF, like you can derive it, right? You can derive the formula, but EF is here, right? So basically it is this angle minus this angle of sine. Okay, that is what how we derive. You can derive this value, you can find out the I, right? Current I, and from there you can derive it. I am not deriving it, I am very lazy. Okay, so this will come out to be negative, right? EF Vt. Okay, let's wait. I will not write this. I know you will get confused. Let me derive it. Let me derive the expression. Although I have actually derived this expression previously as well. Okay, still let me derive it. नहीं तो आप मेरे को पागल कर दोगे. कैसे हो गया? Negative कैसे लिख लिया आपने? कैसे negative लिख लिया? Let me derive it. So this is the I current. So basically, right, your I current is negative actually. Previously, whatever we derived, your I current here, right? Your I current here, right? IS current here. What was it? It was Vs delta minus Vr delta. Here it is opposite. Here it is Vr0 minus EF delta. So it is opposite. That's why a negative sign. But I know आप नहीं समझोगे, दिमाग खराब करोगे. तो let me derive it. So I will derive it. So what is my I? I is Vt angle 0 minus EF angle delta divided by X. Okay, so this will be Vt angle 0 minus EF angle delta divided by X. So this will be basically, this is my I, right? So what will be my power input to the motor? It will be EF angle delta into the current conjugate, right? Vi conjugate basically. So EF angle of delta I conjugate will be like X will be in the, so J is also there, right? Don't forget the J, don't forget the J. So J will be there, this will be minus 90, this will be plus J, this will become plus J into Vt angle 0 and conjugate of EF angle minus delta, right? So my this will be EF, so EF into Vt and plus 90 is there, so 90 plus delta, 90 plus delta divided by x minus EF square plus delta minus delta will get cancelled, 90 divided by x. Now what will be the active power from this? Active will be cos of this, right? Cos 90 plus delta. What is cos of 90 plus delta? It is minus sin delta, right? So this is my cos delta and this is my sin delta. So my cos of 90 plus delta will be minus of sin delta, right? So I'm adding 90, so it will be minus sin delta. That's why this minus sin delta came. And what about this one? What is cos of 90? 0, right? So that's how this negative came. I hope now I have proven it to you. Now you are satisfied that this will be negative only, minus EFVT x by sin delta. Okay. Now I know PI is what? PI is connected to a motor that is supposed to be a load. So if my PI is greater than 0, then only it will absorb the power, and motor cannot deliver power, right? Motor has to absorb power. So for PI to be greater than 0, my delta has to be negative. If my delta is not negative, it can never be positive. Okay. What about the reactive power? QI. What will be the reactive power? Reactive power will be sine of 90 plus delta. EFVT sine of 90 plus delta. Sine of 90 plus delta is cos of delta, right? Cos of delta. So EFVT by x cos delta minus sine of sine 90 will be EF square by x. So this will be the reactive power. Okay. Now cos delta is always positive. Cos delta is always positive. So what is the condition for overexcited condition? What is the condition of overexcitation? I want, have I done this correctly? EF full square, sorry, what is the reactive power input, right? Yeah, reactive power input, this is the current into EF delta, yes. Okay, so I want my motor to absorb reactive power, right? I want my motor to absorb reactive power, I want my motor to deliver reactive power. So my motor is a load. If it has to deliver reactive power, your reactive power QI has to be negative, then only it will deliver reactive power, right? Otherwise it will not deliver reactive power. Okay, it will not deliver the reactive power. So because the motor is a load, and if a load has to deliver reactive power, the reactive power has to be negative. It has to be negative. It is, if it wants to deliver lagging reactive power. So QI has to be negative if it has to deliver lagging reactive power. Okay, so what I can say is QI has to be negative. So I know, so what is the overexcited condition? If a synchronous machine is overexcited, then QI has to be negative, right? This is the condition for a motor to be overexcited. For motor to be overexcited. Okay, so what I can do is this has to be negative. So this has to be less than 0. So basically if this has to be less than 0, I can say my EF, I can take EF constant, right? So basically my VT by, I can take X also, so I'll write this again. This value has to be negative. So from this, right, I can multiply by X on both sides. I can divide by EF on both sides. So basically my VT cos delta minus EF must be negative. That is my EF must be greater than VT cos delta. So this is the condition for a overexcited synchronous motor. Now I want to derive the condition for overexcited synchronous generator. It will come out to be same. You will see it will come out to be same. So you don't have to remember for motor and generator separately. So this will be the condition for overexcited condition for overexcited. This I have taught in the synchronous machines as well. Excited synchronous machine. Let me derive for the motor as well, for the generator as well. Before that, what is the condition for under excitation? EF must be less than. If it is under excited, that means what? If it is over excited, that means my QI must be negative for a motor. For a motor, my QI must be negative. For a generator, my QI will be positive. I will derive it. Okay, uh, and QI must be positive if it is under excited for a motor, right? So the sign of the inequality will just swap. Okay, and for normal excitation, it has to be equal. So EF will be equals to Vt cos delta for normal excitation, where there is no reactive power change. So basically, where my reactive power, right, Q is 0. This is the condition. So okay, I don't have enough space. So this is the condition for under excitation. Okay, any, be it motor or generator, for both this is valid, and this is the condition for normal excitation. Okay, I hope it is clear. Right now, like I want to derive for the I want to derive for the generator case as well. I want to derive for the generator case as well. It will come out to be same. Okay, so yeah, let me derive it for the generator case. So things will just get flipped. Right here, I will have the synchronous generator that will have a voltage EF angle delta, and this, right, will be my terminal voltage Vt angle 0, and this will be Jx. Okay, so if I again derive the value of the, like I think I have derived the value of the power 4 times. So what is the power at the load side? Okay, receiving end power, sorry, if what is the power sending end power, basically PS and QS. So I want to find out the sending end apparent power. This will be VEF angle delta into I conjugate, right? I conjugate. So what is I here? I is EF angle delta minus Vt angle 0 divided by Jx. So this will be equals to into I conjugate. So this will become actually divided by x plus j whole conjugate. So this will become negative, right? So this, right, will be f square by x into angle 90°, then minus EFVT divided by x EFVT divided by x angle 90 plus delta. Okay, so here what does my PS sending end power is, right? Or let me write this as PSG, right? Generating power. What is my PG? So PG is equals to cos of this. So this will go to 0 and this will be cos of 90 plus delta, which is actually minus sin delta, which is minus sign is already there. So it automatically comes out to be EFVT by x into sine of delta. So your delta has to be positive, which is according to our conclusion, delta has to be positive here because it is the case of generator. And if PG is positive, that means what? PG positive meaning it is delivering. For a source, right, if the active power is positive, that means it is delivering active power. For a load, if the active power is positive, that means it is absorbing active power. What about QG? What is my QG? So QG is equals to okay, sine of this. So this will be EF square by x minus EF VT by x cos delta. So now I want it to deliver I want it to be source of reactive power. That means your QG must be positive, then only it will deliver the reactive power, correct? So QG has to be positive if it acts as a source of reactive power. That means if it delivers, because it is a source, right, it is supposed to deliver, so it will deliver lagging reactive power if QG is positive. That is what we have already established. Now let's find out the condition when QG is positive. QG positive meaning it will act as a overexcited synchronous generator because it is delivering, it is supplying reactive power, right? So that's why it will act as a overexcited, it is supplying lagging reactive power, so it will act as a overexcited synchronous machine, right, if QG is positive. But here if my QI was negative, then it was acting as a overexcited synchronous machine because it is supposed to be a load, so it is supposed to absorb the lagging reactive power, but I wanted to deliver the lagging reactive power, so it has to be of opposite sign, that's why it is negative. Okay, so here if QG is positive, what is happening? QG is positive, so this will be positive, right, this thing will be positive. So basically my EF square, this whole thing will be positive. Okay, so if this is positive, right, that means I can simplify this, this will be EF has to be greater than VT cos delta. Isn't this the same condition that we derive for the synchronous motor for overexcited synchronous generator? For motor as well we got to the same conclusion, right, same conclusion. So the conditions are same. Okay, the conditions will be same basically. So I hope I have proven it to you. Other conditions also you can do, nominal excitation, under excitation, you can do it. Now let's come to the next one, that is synchronous phase modifier. So basically synchronous phase modifiers are nothing, we will just change the power factor of the supply end by adding a synchronous motor, right, and it will operate at some mechanical load. Okay, synchronous phase modifiers are nothing but overexcited synchronous motors which will operate at some mechanical load, that's it. Okay, so if I have a sending end active power and sending end reactive power, right, that will get distributed now. So motor will take some active power, but it will also deliver some reactive power because it is overexcited, so it will deliver the lagging reactive power. Ultimately in the load side all of the power will not go because some of the power has gone to the motor side, so the power will be here, overall power will be PS minus PM. And what will be the overall reactive power? Now some of the reactive power is supplied by the synchronous motor and some of it is supplied by the supply. So here the reactive power will be Qs plus Qi. So your load power PL will be what? Your load power PL will be PM PS minus PM, because bit of the power is going out to the motor, and your reactive power Qs will be Q uh, like load reactive power will be Qs plus Qi. Okay, so that is what your load reactive power will be equals to. Now how do I, like, why is it called the phase modifier? Why is it called the phase modifier? So if I see the supply in, right, if this phase modifier was not there, I see that the whatever was the input power, the same was the supply power. Just hold on. If this phase modifier was not there, then the active power required will be lower, right? Because then my PS will be equals to PL. So so I will do one thing. So what is my PS here? So these are the conditions with phase modifier. So this is the case 2 where there is phase modifier connected. Okay, so what is the supply power now? It is PL plus PM. And what is the supply and reactive power? It has reduced actually. It is QL minus QI. Okay, and if there was no phase modifier, what is my supply power will be same as the load power, whatever the load is demanding, because this phase modifier is not there. Whatever the load is demanding, the power will be delivered by the supply, and the reactive power will be simply equals to QL, whatever is the load demanding reactive power that the supply will deliver, right? So if I draw the power triangle, correct, so let's say this is my active power PL, right, then this is my reactive power QL. Okay, initial, I'm drawing the initial phasor diagram. And this is basically my SL for the initial case. So this is the phi 1 initial power factor angle, right? Now in the second case, what is happening? If I see that the supply power is actually increased from PL to PL plus PM, so now it has increased to PL plus PM in the second case. So this much will be my PM basically, right? And your reactive power actually has been reduced, right, because your synchronous machine is delivering some reactive power. So reactive power has actually been reduced now. Okay, reactive power is somewhere around here. Okay, so this is my reactive power that is QL minus QI basically, because this QI is the reactive power by the phase. Sorry, not QI, actually I should have made this as okay fine, that is QI is not a correct notation, right? QI is not a correct notation. Sorry, should be Q of the motor. Let me do it as Q motor, right? Q motor, QM. Okay, so this will be QI minus QM, QL minus QL minus QM. So now your, what do I see? Your actually phi, right, reduces. Phi reduces. Phi 2. So phi 2 is lower than phi 1. Correct? So it modifies the phase of the sending end. Like this phi is what? It is a sending end power factor angle. Right? If phi 2 is lower than phi 1, what is cos phi 2? So cos phi 2 will actually be higher than cos phi 1. Angle and the cos follows a inverse relationship. So cos phi 2 will be higher than cos phi 1. So basically what is happening, with the help of synchronous phase modifier, the power factor improves. Right? So that is what a synchronous phase modifier is. That's it. So this was the required theory basically. We are done with the theory. Now we can do with the questions. Just what will happen, few formula changes will be there, right? So what is my generally I know this formula. This formula we have derived, that my Q is equals to P tan phi 1 minus tan phi 2, but there will be few changes in the formula, okay, because your P has changed. So in the case 1, what was your P? In the case 1 your P was, P1 was PL. In the case 2, what was your P? P2 is PL plus PM, because the motor is also absorbing some active power because a mechanical load is connected. So your Q formula, your QS formula will basically be equals to PL tan phi 1 minus PL plus PM tan phi 2. Okay, so this is the reactive power that will the sub source will deliver after power factor, to improve the power factor from cos phi 1 to cos phi 2. Okay, so if you want to remember the formula, you can remember the formula, or you can again do by basics, right, which we had done in the previous lecture. Okay, so this reactive power is the reactive power delivered lagging reactive power. Remember this, all this is lagging reactive power. Lagging reactive power delivered to improve the power factor from cos phi 1 to cos phi 2. Okay, cos phi 1 to cos phi 2, that is what the lagging reactive power that we will require. Now there are few more power factor improvement techniques, like we can connect the not power factor, voltage improvement techniques, right? We can connect a series capacitance. So this is again a voltage improvement technique, not power factor, actually voltage improvement technique. How? So what is the voltage regulation formula? If you remember, what was the voltage regulation formula for a simple small transmission line, sorry, short transmission line? The voltage regulation formula, if you remember, it was basically r rpu cos phi plus xpu sin phi. Okay, so I want my voltage regulation to be as low as possible, as minimum as possible, so I have to reduce my xpu. So x is inductive. If I connect a capacitance, right, overall xpu will simply go down. Okay, overall xpu will simply go down. Now this is good for voltage regulation. Okay, good. So series capacitor is for good for improving voltage regulation, but it is not good for improving the fault current. Okay, why? If I connect a series capacitance, right, overall fault current will increase to a very high value. How? If you see that, what is the what is the fault current formula? If I have a generator here, and this is the transmission line, and if some fault occurs here, right, previously it was only plus j, now with the help of a series capacitor it is now plus j minus of j xc, right. So here the fault current was magnitude of the fault current was ef angle x. Here the magnitude of the fault current will be ef angle magnitude of x, basically magnitude of x minus xc, right. So fault current increases hugely, here it is lower, so that's a drawback. So series, a capacitor in series, a capacitor in series increases fault current. Okay, so yeah, that's a hit, but stability actually improves. We know what is stability formula. Stability improves, right. What is stability? Stability is Pe is equals to ef Vt by x. So overall, if your reactance reduces, right, your stability, of course, like Pe max, right, steady state stability limit, Pe max will increase. So adding a capacitor in series increases capacitor in series with the transmission line, increases the transmission line, increases the what do you call, the steady state stability limit, steady state stability limit. So that's a good thing actually. So these are good things, right, this point 3 and this point, right, but this is a bad thing, this is a bad thing. Okay, so there are drawbacks and advantages of connecting a capacitor in series. So now we will do few questions and then we will basically wrap up this voltage regulation, sorry, what this power factor improvement chapter. Okay, so this is a GATE 2018 problem. Consider two bus power system with given loads as shown in the figure. all values shown in the figure are in per unit. The reactive power supplied by the generator G1 and G2 are QG1 and QG2. Okay, so they are supplying QG1 and QG2. Okay, the per unit values of QG1 and QG2 and line power loss Q loss respectively are. So QG1, right, like we are delivering, generators are supposed to deliver some reactive power. Generators are supposed to deliver some reactive power. So here I am delivering QG1 and here I am delivering QG2. So the supplier of reactive power is only G1 and G2. So overall available reactive power is how much? It is QG1 plus QG2. That is the overall available reactive power. Now they are asking me what is the reactive Q loss here, what is the reactive power that has been wasted in this inductor, because this inductor also will consume, like this transmission line is inductive in nature, so this will also consume some reactive power. Now what do we notice, that this is delivering 5 pu of active power and this is absorbing 20, right? This needs 20, so this needs only 15, so additional 5 will come here, right? So from here, what is the power transfer, what is the P? P is 5 unit actually, 5 pu, because this needs 20, from here I am delivering 15, so another 5 needs to come from here. So PE, right, across these two terminals is 5 pu. From this I will be able to find out my delta. So if I know my delta, I will be able to find out my reactive power from this, right? I will be able to find out my reactive power. Okay, so I know my PE, that is 5, that should be equals to magnitude of Vs, magnitude of Vr divided by x into sine of delta. Okay, so this will be 1 sine of delta, x is 0.1, so this will be 10 sine of delta equals to 5, right? So your sine of delta equals to 0.5, or your delta equals to 30 degrees. Okay, so yeah, that is the case over here. Delta will be equals to 30 degrees. Now what is the reactive power? What will be the delivered reactive power? So we can find out the delivered reactive power, right? Reactive power loss, that reactive power that will come from this point to this point, because this also will deliver some reactive power, right? So what is QR? If you remember what was Q, like I want to write the expression for QR, right? I want to write the expression for QR. What will be QR? The reactive power that is received at this voltage from this transmission line, right? From this voltage source. So what will be my QR at this node? The QR at this node, right? QR at this node will be, if you remember the formula, it was Vs Vr by X. Remember, I am asking for the reactive power at the receiving end, and receiving end is supposed to be load. Receiving end is supposed to be load, and whenever I write the formula for receiving and reactive power, the receiving end voltage will be squared. That's how you remember, right? That's how you remember that the receiving end voltage will be squared by X. So that's how you remember that if I am writing the receiving and reactive power, the receiving end voltage will be squared, and the term without the square will come with a cos, and the term without square will come with a cos of delta. That's how you remember this formula. Okay, so this will be delta, I know 30, so this is basically 10 root 3 by 2, that is 5 root 3 minus 1. Vr square is 1 into 1 divided by 0.1, so that is my QR basically. So I know my QR, so it is supposed to receive the reactive power, so it will be positive. QR is coming out to be positive, so QR here is coming, right? lagging reactive power is coming from here, it is supposed to receive this reactive power, and QGT is also coming, QR is also coming, QGT is also coming, it is supposed to receive the reactive power here. So both of this will get added to 10 because that is the reactive power at this of this load, right? It should match the reactive power values. So my QR receiving and reactive power plus QG2, right, whatever the reactive power generator G2 is delivering, that shall be equals to my 10, whatever is the reactive power demand of this load 10, right? So I know what is my QR, that is 5 root 3. So my QG2 QG2 will be 10, okay, QR will go there, so this will become 11 minus 5 root 3, okay, that is what your QG2 will be equals to. So if I calculate this value, right, if I calculate this value, this will be 5 into root 3 plus 11, so it comes out to be 2.34, okay, that is what your am I correct? QG2 2.34, right? Well, I'm making some mistake because 2.34 is not in the option. What am I doing? So QR is this, right? QR is this value, cos 30 is 10, 5 root 3, this is, oh sorry, what am I doing? This is not 1, right? This is 10 actually. That is what happens when you try to do shortcuts. Don't do shortcuts. So 5 root 3 minus 10, so this will be, QR will be minus 10, so this will become actually there 20 minus 5 root 3. What am I doing, man? So it is 1 into 1 divided by 0.1, so it becomes 10, right? What am I doing? So 20 minus 5 into root 3, so 11 point 0.34, okay, per unit. So here one thing I forgot to mention, right? QR, right? It is the reactive power at the receiving end. So how much is the available reactive power at the receiving end? Okay. What will be the Q loss? Q loss actually will be, Q loss will be what? Q loss will be the difference of reactive power. Whatever I'm sending here, QS minus QR. That will be my Q loss because this inductor also will consume some reactive power. I'm sending some reactive power here. I don't care whether it is negative. For now, just I know it is negative. Okay. For now, let's just focus on the basics. So I'm sending some receiving reactive power here. Sorry, I'm sending some reactive power from the sending end. Then I have this inductive link. Then I'm receiving that reactive power. So some of it will be lost here in the inductor, right? Similarly, like same condition is there, right? So let's say I'm sending some power here, PS. Some of it will be lost in the resistor, then I will receive it at the load receiving end, correct? But whatever lines we assume to be lossless because your R is 0. So that's why your PS is same as PR. But your QS and QR will not be exactly same because this inductor will consume some reactive power. So we have to find out this Q loss, that is reactive power consumed by the inductor. Okay. So for that I have to find out the QR, that is the receiving end reactive power. Then I have to find out the sending end reactive power. What will be the sending end reactive power? QS. Same formula, but I am calculating the sending end reactive power. So it will be Vs whole square, right? So Vs whole square will be there, and this will come first because why Vs whole square will come first? Because magnitude of Vs is always higher than magnitude of Vr. So that's why Vs whole square will come. That is what we have derived, right? I hope you remember what was the sending and reactive power. That is what we derived. Where did it go? Yeah, here. You see how to remember. First of all, how to remember this? I'm calculating the sending end. So sending end should be squared. The other term VSVR by X should be with cos delta, and as my magnitude of Vs is greater than magnitude of Vr, so magnitude of Vs square will be first. Okay, just like if you see here, right, receiving and reactive power, as I am calculating receiving and reactive power, so Vr will be with whole squared and my other term will be with cos delta, and my magnitude of VR is less than magnitude of Vs. That's why this will be at the lower, because negative is there, right? So this will be lower and this will be higher. Okay, higher minus lower. So that's how you remember the formula, or you can derive it. It will take you 1-2 minutes. Okay. So this will be magnitude of Vs whole square minus Vs VR divided by x cos of delta. So delta we already know, delta is 30, right? So this will be 10 minus 5 root 3. So what is 10 minus 5 root 3? So 10 minus 5 root 3 will be 10 minus 5 into root 3, just 5 into root 3 plus 10. So this will be 1.34. So I am actually sending 1.34 pu of reactive power, right? But I am receiving actually negative reactive power. So what will be the loss? So Qs will be equals to whatever is the receiving and reactive power plus the Q loss, right? So it's same as, what is PS here? Source has to supply. Source will be P loss plus PR. So some of it will be lost in the resistor, some of the active power. Then it will be, the remaining will be delivered to the receiving end. Here, right, there is no active power loss, just there is reactive power exchange. So some of the lagging reactive power will be consumed by the load, inductive load, and the rest will be passed on to the receiving end, right? So from here I know what is my what is my QS? QS is 1.34 minus QR, and QR itself is negative, right? Minus 1.34. Please be mindful of the sign. Be mindful of the sign. So this will be equals to 2 into 1.34, which is 2.68. It is coming out to be positive. Is that expected? Of course it is expected, right? Of course it is expected, because my inductance has to absorb some reactive power, so that's why it is coming out to be positive. Okay, so 2.68, that is the Q loss. Now we have to calculate one more thing, right? What is the other thing? Other thing is, how much is the Qg1? So Qg1 will be what? Qg1 will be the power delivered by this generator, reactive power delivered by this generator. That will be equals to whatever is the reactive power sent to the transmission line plus J5, right? Whatever is the reactive power demand of the load. So Qg1 will be equals to Qs sending in reactive power plus your load reactive power, that is plus 5, right? So Qs is 1.34, right? So your Qg1 will be 6.34 per unit. This question is actually pretty good. So actually what is happening in the circuit? So actually what is happening is, I have this inductive link, right? Whatever is this Jx, and then I have here Eg1, and then I have my Eg2. Okay, so both of them actually are delivering. Eg1 is also delivering some reactive power, and your Eg2 is also delivering some reactive power. If you see here, right, your Qg2 also comes out to be positive, and your Qg1 also comes out to be something positive. So both are actually delivering reactive power, both the generators. Okay, I hope it is clear. And one more thing, both the transmission lines are actually delivering reactive power. Here, right, it is supposed to receive the reactive power, but your QR is coming out to be negative. So actually what is happening, this line, this terminal is also delivering reactive power to the inductance, and this also is delivering reactive power to the inductance. So overall it is becoming 2 into 1.34. So that's why it came out to be 2.68. So option C will be your correct. So this will be your Qg1, this will be your Qg2, and this will be your Q loss. Okay, this was actually a very good question. Let's now solve the next question. So a 2-bus power system in the figure is shown. It supplies a load of 1 plus J5. The value of V1 in P1 delta 2 will be what? Okay. So here I have another inductive load, so that will only consume purely inductive load, right? So first of all, let me calculate the power transfer, active power transfer. Active power, right, at this bus will be 1 pu, because there is no real components, real elements. So whatever active power I am sending here, same will be received here. So what is my PE? PE is magnitude of Vs, magnitude of Vr by x into sine delta. So magnitude of Vs, magnitude of V, I don't know what is magnitude of Vs, is simply V1, that is at 0 angle, and your bus 2 is at receiving end, bus is at delta angle with magnitude 1 divided by x. X is given to me, that is j 0.1 into sine. Remember this delta, right, is supposed to be actually this delta. If you remember, this delta was when the delta was at the sending end, but here it is at receiving end. I have derived it. Okay, I will not derive it again. It actually is supposed to be the sending end phase angle minus the receiving end phase angle. So sending end phase angle is 0, right? Here sending end phase angle is actually 0, that is the actual formula, and receiving end phase angle is delta 2. So this will be 0 minus delta 2. Just be careful regarding that. 0 minus delta 2, delta 2, 0 minus delta 2. So your actual formula is sending end phase angle, sending end angle, sending end power angle minus receiving end power angle. Okay, so V1 into 1 divided by 0.1 sine of minus delta 2, okay, which is equals to 1 per unit. Okay, so I get the value of V1 sine delta 2, that is equals to minus of 1. Okay, basically your delta 2 must be negative, right? Your delta 2 must be negative, and you can see from the options, right, there are a few positive answer. So be careful regarding that, right? If you use simple formula, your delta 2 will be positive, right? Just be careful. If you just use sine delta formula, delta 2 must be positive, but no, it is not positive. It has to be negative, because power always will flow from higher angle to lower angle for a inductive load, inductive link, for a inductive link. Okay, now what about the reactive power at the receiving side, QR? So this was the PR, right? What about QR? So QR, right, again it is magnitude of VR whole square divided by x, right, because I am calculating the receiving side, and it will be in the negative sign because VR is less than VS, and here I will have VS VR, magnitude of VS VR divided by x into cos of, actually it should be cos of minus delta 2, but it does not matter because cos of minus theta is same as cos theta. So here, right, whatever delta 2 sign you choose, it does not matter. So I can write simply cos of delta 2 minus, okay, that is equals to receiving and reactive power is supposed to be 0.9 because it will deliver 0.5. So Vs is V1, Vr is simply 1 divided by 0.1. Sorry, this is 0.1, right? So this is supposed to be 0.1 actually, yeah, divided by 0.1 into cos of delta 2 minus Vr whole square, that is 1 divided by 0.1 equals to 0.5 basically, right? This is 0.5. Okay, so this will be V1 cos of delta 2 will be equals to 1 plus 0.05, so 1.05. okay, so V1 cos delta is supposed to be 1.05, and V1 sin delta is supposed to be, so sin delta 2 is supposed to be minus 0.1. So you have to go by the options. Okay, You have to go by the options. You cannot directly solve this. You can, okay, we can solve this, right? Why we'll go by the options? If I take the ratio of 1 and 2, if I take the ratio of 1 and 2, what will happen? 1 divided by 2, right? That will be basically tan delta 2 will be minus 0.1 divided by 1.05. So 1.05 into 0.1, so it comes out to be minus 0.0952. okay, tan inverse of this comes out to be minus, so your delta 2 comes out to be minus of 5.44 degrees, which is present in the option C, I guess, right? If I see in the option C, it is, sorry, option B, it is present. Okay, and what about the V1? So V1, again, you got the delta 2, so you can replace it either here or here, anywhere you replace. Your V1 will roughly come out to be, because your delta is very low, so your cos of 5, right, will roughly be 1, so your V1 will roughly be equals to 1.05, that is present in option B. So option B will be a correct answer for this question. So with this we end our chapter, that is power factor improvement and voltage control. So I hope you have enjoyed this lecture. If you did, uh, just comment down below and let me know you enjoyed. So I will meet you with another lecture. Until then, happy learning. Hi everyone and welcome back to PrepFusion. So today we will start with lecture 31 of power system. So today we will discuss about economic load dispatch. What does economic load dispatch means? So let's say I have two generating stations, right, and I'm delivering a load demand PD. So my PD must be equals to P1 plus P2. Okay. Now initially I am assuming that there is no losses on the line. So whatever power I am sending, I am receiving at the load side. So initially my assumption is, in the next lecture we will take losses also, we will consider losses as also, but initially I am assume no losses. Okay. Now what happens is this generator G1, right, will have some cost, right, C1 to generate power P1. Generator G2 will have some cost C2 to generate the amount of power P2. Same like to generate 10 megawatt of power, it might cost me 1000 rupees, right? Here to generate 5 megawatt of power, it might cost me 100 rupees. So the costs, right, will be different depending on the type of the generator and stuff. So in economic load dispatch, as the name suggests, what is the most economic way to cater this demand? Basically, what should be the ideal load sharing between the two generating stations, so that my cost of generation, right, and cost of providing this power, providing this demand is the lowest. That is what we will study in this whole economic load dispatch. So what does your cost depends on? So to allocate power generation among available generating units such that the total fuel cost is minimized while still meeting the load demand and operational constraint. So what does my total cost equals to for a generating station? It is the fuel cost plus the maintenance cost plus the service cost. Now generally your fuel cost, your maintenance and service costs are fixed. It does not depend on load. Okay, not a function of load. So these are constant. For nuclear power plant, this will be constant. For thermal power plant, this will be something different, but constant. It will not depend on load. So not a function of load. But your fuel cost, of course, will be a function of load, right? Why will it be a function of load? Because as the load increases, so I have to provide more fuel input. Like let's say it's a thermal power plant. So if I had to generate 1 megawatt of power, maybe I had to give 1 kilo of coal. Okay, but if I have to generate 10 megawatt of power, I have to give 10 kilo of coal, 10 kg of coal. Just a like hypothetical example. Okay, so this, right, we have to actually consider this one. That is the main thing. because these will be constant, these anyways do not matter. So fuel cost is the dominant and the variable component depending on the amount of the real power generated. These are usually fixed maintenance and service cost over short operation periods. So ELD will mainly focus on minimizing the fuel cost. What combination will help us in minimizing the fuel cost? We will see with example. You will understand that even better. Okay. So what do we do in ELD? So ELD basically is called as economic load dispatch. It is a short form for economic load dispatch. Only real power is optimized in ELD. Okay, only the real power will be optimized in ELD. Reactive power is controlled separately with VAR compensator, and we have already seen how to control the reactive power in the previous lecture, right? I hope I don't need to explain again. Generators will operate within their capacity limit. Now, what does this mean? So every generating station, right, will have a lower limit, PG lower, and a upper limit. Okay, every generating station will have a lower limit and an upper limit. Why? Because let's say I have a nuclear power plant, right? So if I have a nuclear power plant, okay, I'm just drawing it off diagram here. You cannot go below its base load, I mean below its lowest load. Why? Because what we do, we always have some fuel on the pipeline, so it always flows through the nuclear power plant. I cannot make the load suddenly go to zero, right? So it will have some base load that I cannot go below that. So that's why it will have a lower limit, right? Otherwise the plant will not function properly. And of course, if the rating of the power plant is 100 megawatt, it cannot deliver beyond 100 megawatt. It has to be below this value, right? It has to be below, so it has to be below 100 megawatt. If I try to deliver 100 megawatt, more than 100 megawatt power from this power plant, it will be a problem to us. So that's our range, right? So this will be given to you, this range will be given. So economic load dispatch, it takes into account it basically optimizes the active power cost. We don't control reactive power, and it also takes into the fact that there is a constraint of operating limits. I cannot go beyond my upper power generation, I cannot go below my upper power generation. Okay, so now there are a few terms that we must understand. Okay, the first term is unit commitment. While ELD determines how much power each generator should produce, unit commitment answers the question which generating units should be on or off at any given time to meet the forecasted demand economically and reliably. So unit commitment tells me which units will be committed, which units will be on to cater the required power demand. Okay, so your unit demand, right, your UI will be either 1 or 0 into the power delivered by that particular generating station. Okay, so UI will be equals to 1 or 0, it will be 1 when its unit is in operation. So let's say if P1 is in operation, right, let's say if P1 is in operation, P2 is in operation, P3 is not in operation, P4 is not in operation. So my PD is P1 plus P2, or I can write PD is 1 into P1 plus 1 into P2 plus 0 into P3 plus 0 into P4. Okay, so your like this will be summation of UI and PI. So these are 0, so these units are turned off and these units are turned on. So that is what my unit commitment tells me. So it ensures that enough generating units are online to meet the demand, plus few reserves will be there. Okay, like we don't need to turn on all the units, right? We don't need to turn on all the units because that will be just a waste of power. That will be also waste of resource, because ELD, right, the higher the number of generators, ELD will be a bit difficult to calculate. Okay, so unit commitment just tells me whether this generating station will be on and off. So on and off, so it's a binary decision. ELD is a continuous optimization problem. Like if the generating station is on, then how much power will it send? That's a continuous power, right? Power can lie between 10 to 15 megawatt. So that's a continuous range. Unit commitment is just a discrete value, 0 or 1, on and off. Okay, now there is another term known as heat rate curve. What is heat rate curve? It represents the amount of fuel energy in kilocalorie or BTU required to generate 1 unit of electrical energy. Okay, so I can show you example. Here we have the heat rate curve basically. So how much like this is the power generated, right? Pi is the power generated. Okay, Pi, sorry, oh, this hyperbola should be actually here. Pi is the electrical generated, right? So basically it is the amount of heat required to produce this much amount of power, electrical power. That is what my heat curve is. So maybe remember, this is the unit of this is mega kilocalorie per megawatt hour, and this is in megawatt. Okay, because this, right, fuel energy, this will be, okay, mega kilocalorie, the unit should be mega kilocalorie per kilowatt hour. So remember, like, the thing is that initially, right, to produce on less amount of power, let's say 10 megawatt of power, maybe per megawatt hour of power, I need more heat. So because it will not operate at the highest efficiency, right? Our machine mostly it operates at highest efficiency at 70% of the rated load, right? Now the basic thing that you have to understand is what is H. H is the heat rate. It is not the amount of heat. It is not the amount of heat. It is the heat rate. So you might have a natural question, sir, as I need to produce lesser amount of power here, why do I require more heat rate? It is not heat, right? It is heat rate. Heat rate. It is heat rate. What do I mean by it? So basic thing what you need to understand is that basically here, right, it is not operating at its highest efficiency. A machine operates at highest efficiency around its rating. So let's assume that 20, when it is delivering power of 20 megawatt, it is the efficiency is the highest. When it is delivering 20 megawatt, the efficiency is highest. So what is the kilocalorie per megawatt hour, right? Per energy. So here, right, although I am producing lesser amount of power, but to produce that power, right, per megawatt hour, I need more heat energy. Per megawatt hour, I need more heat energy. Okay. So here, right, basically means per megawatt hour, how much heat energy I need. Okay, how much heat energy I need. So that is what we have to find out. Per megawatt hour, how much heat energy I need. Not find out, sorry. That is what we are observing in the graph. So although, yes, here we are generating less power, but to generate that amount of power per megawatt hour, I need more heat. So it is not good actually, right? Here, right, this is the best possible scenario where I need, although I am generating more power, but per megawatt hour, I am requiring less amount of heat, right? So amount of heat required to produce 1 unit of electricity. So it basically means HI basically means amount of heat required to produce 1 unit of electricity. I hope you know what is 1 unit of electricity. It is simply watt hour, right? Watt hour. So here, right, I will avoid working in this region because I need more heat, so I will need to provide more fuel to generate 1 unit of electricity. If I'm delivering, let's say something 15 megawatt of power, but if I'm delivering 20 megawatt of power, the amount of heat required to generate 1 unit of electricity is actually lower. So that is good, right? Because it comes with the factor about the fuel cost function. So lesser the heat, lesser will be the fuel requirement. Okay, lesser the heat, lesser will be the fuel requirement, right? So your heat rate curve, it is just an empirical formula, is defined by like this. Okay, no need to worry about this, no need to remember this, this will not be used anywhere, but empirical formula we have derived in power plant. Generally this is there, like we are actually discussing for thermal power plant because that's what we mostly use, right? So that is a thermal power plant. And don't worry, you don't need to remember this formula. Just for derivation purpose, I need to explain you this concept about the heat rate curve. Okay, so the heat rate curve definition is also given. Total fuel energy input, basically what is the total amount of heat energy produced divided by the electrical power output. Okay, so lower the heat rate, higher will be the efficiency, because I need to provide less energy input to provide to get the same output, right? So like what is efficiency? Efficiency is output upon input, which is electrical energy upon your input, that is the heat energy. So in all the cases, right, in all the cases my electrical energy is 1 kilowatt hour of power, 1 kilowatt hour of power. Okay, so electrical energy is fixed, that is 1 kilowatt hour. Now what I am observing, that if I am lying in this region, right, then basically if my power output is 15 megawatt, then my heat rate is something like 15, right? This is, let's assume this is 15, this value is 15, okay, into 100. And in the second case, when I'm lying in this region, power output is still 1 kilowatt hour, because that is the definition of heat rate, that how much heat I need to provide as input to generate 1 kilowatt hour of energy. So it will be 1 kilowatt hour, and the amount of heat energy will be 20 here, right? So what do I see? So sorry, just give me 1 second. Full energy input, sorry, it is 10, right? It's not 20. So 20 is the megawatt power, right? 20 is the megawatt power. I'm talking about the heat rate. Heat rate is 10, right? So which one is higher? Which one is higher? So of course the second case will be higher, right? Efficiency in the second case will be higher. That's why I am saying this is the optimal place, because I will need to provide lesser amount of input energy to produce the same amount of kilowatt hour. So I need to operate in this, near this region. So heat rate and efficiency are inverse of each other. So lower the heat rate, higher the efficiency. Okay, so heat rate curves will be used to derive the fuel cost. Okay, so we'll derive the fuel cost now. So how do I derive the fuel cost? So my heat rate is this. This is the amount of heat per kilowatt hour, mega kilocalorie per kilowatt hour I need to produce to generate this amount of heat. Okay, so for any unit I, for ith unit, okay, for ith unit, Now what will be the fuel cost? So we have a like conversion, okay, that heat is in kilocalorie per kilowatt hour. So we convert this at mega automatically will be cancelled, mega kilocalorie will automatically be cancelled. I will divide this with the calorific value of fuel, right, because this is the amount of heat energy I need to provide, right. And what is calorific value? So calorific value is basically the amount of heat that it will provide to per kg, how much heat a fuel will provide. So calorific value of a fuel, calorific value of fuel is basically amount of heat produced in mega kilocalorie per kg. So let's take an example of coal. So like don't worry, you don't need to remember all this. So calorific value of coal calorific value, right? Calorific value of coal will be 2 mega kilocalorie per kg. So 1 kg of coal can generate this much amount of heat. So that is what we have to find out. So this is the heat rate. If I divide this by my calorific value, what will be left out? It will be kg per megawatt hour, kg per kg per megawatt hour, or sometimes this is in hour as well, no problem. Okay, kilocalorie megawatt hour, yeah. So I will divide my heat rate with calorific value, right, of the fuel. So mega kilocalorie will get cancelled, just there will be kg per megawatt hour, kg per megawatt hour. Now I got the unit as kg per megawatt hour. Okay, so per megawatt hour, this much amount of kg I need to, this much amount of kg I will require. Now I will multiply. How do I find out the amount? I got the amount of coal, right? So if let's say my HI, right, let's take an example. HI is 500 per mega kilocalorie megawatt hour. Heat rate is this value. Okay, now what I will do, I will divide this by my calorific value. If I divide this by my calorific value, what do I get? I will get the amount of coal required. Don't worry, these things you don't need to remember, this will not be asked. Okay, amount of coal required. Amount of coal required will be this 500 per hour. Okay, per megawatt hour, 500 upon 2, so this will be 250 kg per megawatt hour. Okay, now what I will do is I will multiply this with the rate of fuel. Okay, so I need to find out the cost of production. I need to find out the cost of production. How will I find out the cost of production? So cost of fuel will be, let's say, I don't know, just a rough value, 10 rupees per kg, 10 rupees per kg. Now this is the amount of fuel required per megawatt hour. Let's say I am generating, like at this particular case, right, my generating, right, Pi is equals to 5 megawatt. I am generating 5 megawatt of power. So what will be the amount of coal required per hour? Per hour, how much coal do I require per hour? Amount of coal required per hour, right, per hour will be this value into my Pi, because that will cancel the mega, right, that will cancel the mega. So this will be equals to 250 into, what is the Pi? Pi is 5. 250 into 5, that will be equals to 1250 amount of kg per hour. So this is the amount of coal I require per hour. Now how do I find out the cost of the, I know the cost of the fuel, that is 10 rupees per kg. So what will be the cost of the production? Cost of production cost of production for cost of production per hour for generating Pi equals to 5 megawatt. For generating 5 megawatt of power, what is the cost of production per hour? It will be basically this value, 1250 kg per hour into 10 rupees per kg, right? Per kg I need 10 rupees. So this will become 12,500 rupees per hour. Okay, per hour, this is the cost of production. So from this, what is the conclusion? Now is the important point. What is the conclusion? Conclusion is nothing but my overall cost of production, right, per hour cost of production will be equals to my HI divided by the calorific value, or divided by calorific value, into Pi. Here I have to multiply the power, whatever power I am generating, right, HI, heat rate, into Pi. That is what we did. HI into Pi divided by the calorific value into the rate of fuel. So this much only you need to know. So I just shown with example how can we find out this cost of production. Okay, so this is the thing that you need to understand. That's it. Okay, so yeah, that is the key conclusion. So this, right, so I need to multiply HI into Pi. Okay, so HI, if I multiply HI into Pi, what will happen? So already like my heat rate function is alpha 1 by Pi. So your cost function, right, this calorific value is a constant, right, it will be constant. Rate of fuel also is a constant number. If I multiply Pi, this will become alpha 1 plus beta 1 Pi plus gamma 1 Pi square. So your cost function, right, as a function of Pi becomes this. Like we just change the constant, alpha 1 become A because these are all constants, right. So this multiplied by alpha 1 will become A, then I will have B into Pi or Pg, whatever you want to say, plus C into Pg square. Roughly the conclusion is your cost function will be a parabolic function. That's it. Your cost function will be a parabolic function. That's it. So the nature of the cost function will be a quadratic or parabolic. That's it. Okay, that is the conclusion. No need to understand anything else. Okay, so your CPG will be the fuel cost per hour, the amount of fuel cost per hour. PG will be the power generated in megawatt or whatever unit they have given. EBC all will be cost coefficient. Now to like achieve optimal dispatch, we have to follow this condition. How, I will explain that, don't worry. But for now, one more thing is there. Your fuel cost will vary like this function, but remember I have told you that your range of power must lie between Pmax and Pmin. It cannot go below Pmin, it cannot go above Pmax. Okay, in both these cases generator will be on the verge of instability. So basically if I am here, right, if I am lower than my Pmin and if I am here, then generator loses synchronism. Okay, you have to be mindful of that. Now one more term is there regarding the incremental cost. What does incremental cost mean? Basically, how much does my cost vary with variation in the power generated? So my incremental cost, also known as IC, is basically the change in the cost variation with respect to power generation, right? It is basically DPI, incremental cost of unit I will be DPI by DCI. Okay, that will be your incremental cost. What will be its unit? So this is basically, its unit is cost rupees per hour, right? Or its unit is rupees per hour. So what I'm doing, I'm just dividing, sorry, I have written it the opposite way around. It will be DCI by DPI, right? DCI by DPI. So basically your cost will be divided with by power, so this will become rupees per megawatt hour. Okay, because pi will be in megawatt hour. So in this case, what is the incremental cost? In this case, right, I am differentiating a is just a constant number with respect to pi, that will be 0. I am differentiating this b into pg, so that will be b plus 2c p I. Now it might change, right? It might change if the fuel cost function is different, but mostly fuel cost function will be this only. So your incremental cost, right, is a linear function. Your slope is a linear function. So it is rupees per megawatt hour. Okay, it's a linear function. So your incremental cost will be a linear function, and from this, right, we will get the condition for like for unit I. This is for unit I. We'll find the optimal cost. What will be the optimal cost? Optimal cost will be where the incremental cost is equal, basically, like, sorry, where the incremental cost is equal for all the units, whichever one are active in power generation process. Okay, so we can understand this with a very basic uh, example. So this, right, this condition is nothing but Lagrange's condition. Okay, Lagrange actually thought of this condition, that how can my function be maximized. So this condition is known as Lagrange's method. Lagrange's, am I doing the spelling? Yeah, Lagrange's method. Okay, so how is it possible that if their differentiations are equal, we get a maximized condition? This we can take example, right? Let's take an example. We have to find the maximum area of a rectangle that can be fitted under the ellipse with following equation, right? It is just a standard equation of ellipse. So what will be the maximum rectangle that will be fitted in the ellipse? So what is the like, how is the ellipse shown? So ellipse will be shown something like this, right? This will be my rough ellipse. Okay, Now the maximum rectangle that can be fitted will be somewhat like this. I don't know exactly maximum area of the rectangle. Okay, so this will be the maximum area of the ellipse, correct? So what will be this, like what will be the coordinates here? So this coordinate will be my x comma y, right? And if it's a rectangle here, right, both of them will be at same height, so y will be same, x will become minus x because it is symmetrical about the origin. So this will be minus x into y. This will be what? This will be minus x into minus of y, as it is symmetrical about the origin. This will be x into minus of y. Okay, so now what is the overall area? So this, how much is the side here? It is 2x. How much is the side here? It is 2i. So my area equals to 2x into 2y, that is 4xy. Okay, so my area is 4xy. I have to find out I have to maximize this area. And what is my constraint? Constraint meaning what is your cost function? Your constraint is x and y must lie in this curve, right? So your constraint is basically constraint. This is the function that I have to maximize. And your constraint is this, that your x square a square plus y square by b square must be equals to 1. Okay, so what we can do is we can write this, that my x square by a square plus y square by b square minus 1 equals to 0. This is what we can write, right? So I can write my area, actually area function, something like this. It is 4xy, it will be 4xy obviously, plus, sorry, not plus, I can write minus or plus, whatever you want to, minus lambda into x square plus y square divided minus 1, right? Why? Because this is anyways, this will always be anyways 0, so my area does not change. Now what I will do, I will differentiate this function with respect to x, and I will differentiate this function with respect to y. Lambda is just a constant number. Lambda is just a constant. Lambda is just a constant. Okay. So if I differentiate this function, partially differentiate this function with respect to x, what do I get? This will be 4y minus lambda into 2x divided by a square, and if I partially differentiate this with respect to y, this will be 4x minus lambda into 2y divided by b. Okay, now we know the condition for maxima is both of them has to be 0, right? This we have studied in maxima minima, the partial derivative, both of them has to be 0 for either for maxima or for minima. Okay, so from this I get the values, right? What do I get? I get that my lambda so I can copy this thing, right? This has to be 0. So if this has to be 0, that basically means my lambda into 2x minus a square equals to 4y, and my lambda into 2y by b is equals to 4x. Okay, so now what I can do is I know these equations, right? And another equation I know, that is, what is the other equation? That is x square by a square plus y square by b square equals to 1. This is the constraint equation, right? If I divide these two equations, what do I get? If I divide equation 1 and equation 2. So if I divide equation 1 and 2, what will I get? It will be y by x equals to x by y, this is b square, sorry, this will be b square, right? X by y into b square by a square. Okay, so from here I get my one of the equation, y square equals to x square into b square by a square. So I can replace this value over here. If I replace this value over here, what do I get? I see that this will be equals to x square by a square plus x square by a square equals to 1. So x comes out to be plus minus root 2a. Okay, x will come out to be plus minus, not root 2, sorry, a by root 2. And similarly, your b will come out to be plus minus b by root 2. Sorry, your y will come out to be plus minus b by root 2. So these will be the values of your x and y, and what will be your maximum area? You can choose either both positive, both negative. You cannot choose both to be 0, right? So your maximum area A is coming out to be a by root 2, 4 into a by root 2 into b by root 2, that is 2ab. That will be your area, maximum area. Okay, now what is lambda? What is the value of lambda here? So value of lambda is equals to what? Value of lambda equals to 2 upon y by x upon a square, right? Which is equals to what is 2 upon y by x? So what is y by x? So y by x, right, if both are negative or both are positive, it will be b by a basically. So this will be 2 into b by a. I'm choosing either both to be positive or both to be negative. Okay, both to be positive or negative. So b by a into a square. Correct? Y by x, yes. Divided by a square. Am I correct? Sorry. A square will get multiplied over there. Sorry, it will be multiplied by a square, not divided by a square. Right? So this comes out to be 2ab. Right? So how can it help me in power system? So I will actually not assume this as my fuel cost function, because here, right, my I will not be able to write it in terms of my PG. What I will do is, or I can still write it in terms of PI, right? Yeah. So I will have this fuel cost function here, right? So what will be my total cost? Total cost will be summation of C of I of PI for units from 1 to n. Whatever the number of units are there, that will be my total cost of the function. So for plant 1 it will have some Ci, for plant 2 it will have some Ci, each plants will have some Ci. So this is the first equation, right? This is the first equation. Second equation is what? That is a constraint equation, that is the summation of power delivered by all the plants from 1 to n, right? Pi will be equals to my demand, Pd, correct, considering no losses, assuming no losses. Okay, of course we will come to the losses factor as well, but for now considering no losses, this will be the overall power summation. This will be the constraint. Basically overall summation of power of all the plants should be equals to my Pd, right, constraint. Now again I will do the same thing. What I will do, I can take this on the left hand side, I can take the Pd on the left hand side. Okay, so the constraint is basically my I into n into Pi minus Pd has to be equals to 0. So what I can do, I can write my overall cost function. I have to minimize. So this Lagrange's method can be used to both minimize and maximize, or minimize or maximize. So Ct, overall cost function, total cost function, right, is equals to what? It is equals to summation of I equals to 1 till n Ci function of Pi minus lambda into summation of I equals to 1 till n Pi minus this Pd, right? Now for maximization, what do I need to do? I need to simply differentiate this equation, right? I need to differentiate del Ct upon del Pi. Now I have to differentiate with respect to different values of y. Here I differentiated with respect to x and I differentiated with respect to y because my function, my minimizing function was a function of x and y. But here I have to differentiate with respect to one, then I have to differentiate with respect to 2, and for all of those cases ultimately the final value will come out to be equals to 0, because that is the condition for minimization or maximization. So in this case we will get the minimization only, don't worry, we will get the minimum condition only. Okay, so here, right, I have to put I equals to 1, then I have to differentiate this whole function. If I differentiate this whole function, what will I get at I equals to 1? So this will become del C1 of P1. Basically del C1 is a function of P1 only, that is understood by us. That will be equals to del P1, okay, minus lambda. Now I'm differentiating P1 over here, right? I'm differentiating with respect to P1. I is 1, right? So what is the differentiation of P1 with respect to P1? 1. What is the differentiation of x with respect to x? 1. So this will be 1 minus 0. Why this will be minus? Because your load demand is not a function of input power, right? It is a constant function. It is independent of input power. So it is independent of input power. So that's why this will be 0. So from here I get the condition, this has to be equated with 0. From here I get the condition del C1 by del P1 has to be equals to lambda. Similarly, you will get the same equation, del C2 by del P2 will be equals to lambda, and this will go on, right? This will go on. So basically what I can say, lambda, all the incremental cost, right, of plant 1, like this is what, this is the incremental cost, that is what we derived here, right? We derived it over here. Okay, why is not, why is it not moving upwards? So your incremental cost is here, that is equals to IC. So this is my IC basically. So all the incremental cost must be same. IC1 must be equals to IC2 must be equals to IC3 and so on. All the incremental cost must be same for the units to operate in for minimum cost function. Okay, so for minimum, the conclusion is minimum fuel cost function incremental cost fuel cost of all the plants must be same. Okay, so they must be same for incremental cost. So basically this is what Lagrange derived. So from this, right, this condition came basically. So I hope it is clear. So we will solve few questions, and through this we will understand, like, you don't need to understand that, like, if you understand the derivation it's very good, but you just need to understand, remember the conclusion. We just need to remember the conclusion, that's it. Okay, so let's solve few questions. So generally either they will give you the incremental cost curve or they will give you the cost. So, and they will give you the limits, right? We will solve with limits, and from there we will understand many things. So the incremental cost curves for the two units, generating units, are given. The total power demand is 200 megawatt. So PD is 200 megawatt, and both generators having operating limits of 100 megawatt and 550 megawatts. So both generators having operating limit, right? Remember, this is very important. You will equate your constraint, you will equate your incremental cost, and then see whether you are going out of range or not. If you are going out of range, then you have to again go back. Okay, so your PG1 and PG2 has a range of this, right? 100 to 550 megawatt. So for most, we have to meet the demand economically. So I have two generating stations, and they are catering the load, and the load is of 200 megawatt, and let's say generating station 1 is generating P1, station 2 is generating P2. So my P1 plus P2 must be equals to 200 megawatt, right? That is certain. And for meeting the load demand most economically, my incremental cost, right, of 1 must be equals to incremental cost of 2. So what is the incremental cost of 1? That is this value, right? 0.012 into P1 plus 8 equals to 0.008 into P2 plus 9.6. Okay, so from here I can directly say that what will be like I can say the relation between P1 and P2. So I can I can divide by 0.04, right? So this will be 3P1 minus 2P2, and if I divide by 0.04, this will be basically 9 point, so 1.6 divided by 0.004 comes out to be 150. Okay, so I can multiply 2 over here, so this will become 2P1 plus 2P2 equals to 400 megawatt. Okay, so this will be 5P1 that will be equals to 550 megawatt. So from here my P1 comes out to be 110 megawatt. Now is this within the range? So P1 actually is within the range, right? 110 megawatt and 550 megawatt, it is within our range. So this is correct. This is fine. This is fine. What about P2? What will be P2? So P1 plus P2 must be equals to 200. So P2 comes out to be 90 megawatt, which is actually not possible. Not possible, right? Why it is not possible? Uh, because the minimum value of the generating power rate is 100 megawatt. I cannot go below this value. I cannot go below this value. Okay, if I go below this value, then there is a problem, right? So I have to choose P2 equals to 100 megawatt, because that is the minimum value, right? That is the minimum value. I cannot go below this, right? So they are telling that for best economic load demand, the value should be uh, the value should be 90 megawatt, but here, right, I'm going below my low range, so I have to choose the lowest value, whichever I can choose, that is 100 megawatt. So this will change my P1. So P1 will now become what? P1 also will become now 100 megawatt. Okay. कम करना चाहिए था actually. Okay, one change I will do actually. One change I will do, because this minima, right, is too high. Why I will explain later on. Like we will not do for this example, for this question we will actually choose the minimum value to 50. Otherwise, the thing that I will explain, you will not be able to, like I will not be able to explain the thing that I want to explain. Okay, this has to 50 minimum. We will choose 50 only for this particular question. So here, right, 77. This has to be 50. It's to be 50. Okay, so why am I choosing 50? So that it can lie within the range. So P2 is also valid in this question. I made it valid. Okay, when this will be invalid, when this will go out of the range, for that condition, for that case also we will solve, don't worry. For now, just let's assume that it is within the range. So now what is the total cost function? What will be the total cost? Total cost will be C1 plus C2, right? And initially, let's assume that initially uh, system was at no load. System was operating at no load. Okay, system was operating at no load. So if system was operating at no load, then so total cost is C1 plus C2. But what do we know? We know incremental cost IC1, right? What is IC1 or IC2? So what will be C1? So what is IC1? IC1 I have found out the value from this, right? From this equation I know P1 P2, I know IC1, right? I'll be able to find out the value. So IC1 will be equals to del P1 divided by, sorry, del C1 divided by del P1. So if I want to find out the total cost, so I have to integrate on both sides. So it will be IC1 integration with respect to P1 will be equals to dP1. So initially the obviously for generating zero power, right? For generating zero power, the cost will be zero. For generating some the power that you have derived, the cost would be C1. So 0 to P1. So your cost, right? Sorry, I meant this will be, sorry, DC1 into dP1. So for generating zero power, I will require zero cost. For generating P1 power, I will need C1 cost, right? I will need C1 cost. So for generating P1 power, I will need C1 cost, right? So this is what we will do. So I will first of all write down the incremental cost equation, and then I will integrate from 0 to P till P1, whatever we have derived, right? So total cost will be equals to integration of the incremental cost, that is this IC1 of dP1 from 0 to P1 whatever we have derived 110 megawatt, right, plus from 0 to 90 megawatt of the IC2, that is this value. Actually both of them will come out to be same value only, so we don't need to connect them, we don't need to calculate them separately. If I just multiply this by 2, or no, I cannot multiply this by 2, no. But this IC1 IC2 will be same value, but their integration can be different, right? Integration can be different, no, yeah. So this, right, I will use this to find out the total cost. So this will be LP2. Okay, so CT will be equals to this will be 0.012 P1 whole square divided by 2. So this will become 0.006 of P1 whole square plus 8 P1. P1 goes from 0 till 110 plus this will be 0.004 P2 plus whole square plus 4.8 P2 till 0 to 90. So your total cost will be 100.006 into 110 whole square plus 8 into 110. So it comes out, this one comes out to be 952.6 plus this will be 90 whole square into 0.004 plus 4.8. Why is this 4.8? This should not be 4.8, right? So this will be 9.8. So I have divided both by half, 9.6. So 9.6 into P2 will be basically 90. So it comes out to be 896.4. So this value comes out to be 952.6 plus this 1849 rupees, okay, per hour. It will come out to be per hour. So that is the cost in case 1 when we considered economic load dispatch. Now let's consider a case, okay, let's consider the case 2 without economic load dispatch. So let's assume a number, right? Let's assume both of them share, assume both share load equally. Now if both share load equally, what will happen? If both share load equally, then my P1 will be equals to P2 will be equals to 100 megawatt. So I will again find out the total cost function this time, right? But this time both integration will go till 100, right? Not 110 and 90. So both of the integration will go till 100. Okay, so this will go till 100, this will go till 100, this will be 0.006 into 100 whole square into 800. So this is okay, y plus 800, so this becomes 860 plus 0.004 into 100 whole square plus 960, so this becomes 1000. So what is your overall cost? 1860. What was our previous overall cost? 1845. So what is the total cost? 49. What is the total cost saving, right? With ELD cost saving, this can be asked in question actually. Cost saving with ELD, it will be 1860 minus 1849 rupees per hour, okay, which is 11 rupees per hour. Now you might feel sir ये क्या है, 11 रुपये क्या होता है? आप तो 250 रुपये में कोर्स भी नहीं खरीदते, आप बोल रहे हो 11 रुपये क्या होता है? No, 11 rupees actually here it is coming out to very low, right? But in real life these are just made up numbers, right? In real life this actual number is very high, okay, which will have a huge impact. So that's why we want to minimize this cost. We want to have economic load dispatch as much as possible, because the cost, right, will be much lower. So we will save huge amount of cost. So that is the cost saving basically in rupees per hour. I hope that point is clear, how we are saving the cost. Okay, so that is what we do basically without loss. My cost function will be C1 plus C2 plus C3, that is CI PI. Then I know this, right, this demand, and by using Lagrange's method we can minimize the cost. What is the Lagrange's method? Simply your incremental cost of 1 should be equals to incremental cost of 2 and so on, right? This is the Lagrange's method to minimize the cost function. Okay, okay, this is the Lagrange's method. This we will equate this with lambda. This will be a constant value, that is equals to lambda. Okay, I hope that part is clear, how we are deriving the things. Let's now solve few more questions. Yeah, let's now solve few more questions. This is the one, this is the one question, the same question only. Okay, initially the power demand here is 250 megawatt, and now like the power demands are separate. So initially in the case 1, right, we have to solve for both cases. Case 1, my PD is actually 250 megawatt. In case 2, what they're telling, that your PD is 400 megawatt. Okay, PD is 400 megawatt. Okay, so what I can say is now incremental cost equations. So we have to find out the condition for maxima. So condition for maxima, right, in the case 1 actually same as the previous question, because here also we equated, right, the demand was 250, here also the demand, okay, sorry, here the demand was 200 actually. Okay, so we have to solve again, so we will solve again, right? So no problem, फिर से करेंगे. So my P1 plus P2 should be equals to PD, that is 250, and my incremental cost, right, has to be equal. So basically 0.012, it is 0.012, right? Yeah, 0.012 P1 equals to 0.08 P2. Okay, 0.01 P1 equals to 0.08 P2. Sorry. Also there is the constant term, right? Yeah, constant term is there. This will be plus 8, and this will be plus 9.6. The incremental cost must be equal for economic load dispatch. So now here, right, I get again the equation 3P1. This equation will be same, minus 2P2 will be equals to 150, and my P1 plus P2 is 250. If I multiply 2 here, 2P1 plus 2P2 will be equals to 500. So from here, if I add the two equations, my 5P P1 is equals to 650. That, so my P1 will be equals to 130. Yes, P1 will be equals to 130 megawatt, and my P2 will be equals to 120 megawatt. Okay, which is in the range. That is a problem. Okay, because I wanted to solve for the case where it will lie out of the range, right? So let me actually, okay, let me keep this at 200 only. Let me not keep it at 250. Otherwise, I will, like, the purpose will be defeated, basically. Purpose of this question. So let me keep it at 200 only. Yeah, let me copy the same question here, right? That will be the best thing. No, I cannot copy. This will be 200. Okay. So if I keep it 200, like, the purpose is, I will explain the purpose just now. So this will be 200. This will be 200, right? 200, 400. This will be 550. This will become 110, and this will become 90. Now the problem here will be, my P2 with economic load dispatch is coming less than, P2 is less than the minimum, minimum constraint, right? So I cannot go below this. My economic load dispatch is telling me that we have to actually make the P2 to be 90, but I have a constraint that I cannot go below 90. I cannot go below 100, right? So my economic load dispatch is telling me to take lower value of P2, but I cannot go below P2, so I will take the lowest value of P2. I will take the lowest value of P2 that is possible, that is 100 megawatt. If I take the lowest value of P2, then my P1 will change to 100 megawatt, because P1 plus P2 must be equals to the load demand, right? So the thing is, the conclusion is, with economic load dispatch, with ELD, my P1, like with ELD, like ELD, for ELD P2 must be 90 megawatt, but I cannot go below 100 megawatt, so I will choose I will choose 100 megawatt, that the minimum value basically. Okay, so like this you find out the most economic load dispatch conditions with some constraints. So here let's do it, let's solve it for P equals to 400 megawatt, right? If my P is equals to 400 megawatt, then it will anyways lie within the range, then there is no problem. Okay, let me change the higher range as well. Let me change the higher range to 150, but 150 won't be possible. Let me change the higher range to 250. Yeah, 250 is good, right? Because so that like I will take the condition for the higher limit as well. I will take both the conditions, both for lower limit and the higher limit. Okay, so let me take it to be 250. Okay, so it will be 250, right? So if I take the upper limit to be 250, right? Now let me solve it for the case of 400 megawatt when I'm servicing catering for 400 megawatt. So if I'm catering for 400 megawatt, so my P1 plus P2 must be equals to 400 megawatt, and of course I know this equation will be again same, incremental cost must be equal. So my 3P1 minus sorry 3P1 minus 2P2 must be equals to 150 megawatt, right? So I can again multiply by 2P1 plus 2P2 equals to 800 megawatt. So if I add these two equations, 5P1 equals to 950 megawatt. So P1 will be 100 590 190 megawatts, which is actually within the range, so there will not be any problem. Okay, I want to go out of okay, how can it be within the range? No, something I'm doing wrong, right? No, this is correct only. Yeah, this is correct only. Okay, so we are servicing 400 megawatts, so that is fine actually. Let me service a bit more, let me service 450 megawatt, right? Because I want to go out of, okay, out of ranges. Let me make it 200 actually. 200 will be still in the range, right? Okay, let me increase the demand to 500 megawatt. Basically what I want to reach the maximum value, so I have to choose the values here. So if I reach 500 megawatt, it will be the maximum value anyways. If I reach 450, yeah, that will be fine, 450, right? Also will be, it's almost, they are sharing almost equal load actually. 190 to 190, that will be 210. 210. Okay, let me make this limit to be 200 here. Okay, so all these have to do just to like make the question, because the question is not perfect, right? So I want to reach the maximum limit and I want to reach the lower limit. So let me make it 200. 200. This is fine. Okay, so if my limit is 200, right, I cannot go beyond 200 value. So my P1 comes out to be 190. What about P2? So P2 will come out to be 210 megawatt. But again, the problem is I cannot go above 200 megawatt, because that is what my limit. That is the liberty, right? That's why I'm a teacher. I can change the question. Okay, so the limit is 210 megawatt. So sorry, limit is 200 megawatt. So I cannot go beyond 200. So my P2 will be constrained to 200 megawatt. Right, and P1 will be constrained to then 200 megawatt, both, because I have to service 400 megawatt of power. Okay, so like these kind of questions will come, right? This here, right, I have to change the numbers, but in other cases you may not have to change the numbers. Okay, in most cases. So let's solve this last question. With this we will end today's lecture, and in the next lecture we will solve for the incremental cost with for the economic load dispatch with losses. Okay, so here we have a cost function for the two generating units are given, and P1 P2, like cost functions are given, incremental cost is not given, cost function is given. The total power demand is 200 megawatt. Okay, total power demand. So what is the cost function? Cost function is C1. Cost function is quadratic in nature, that's why you are seeing quadratic cost function. P1 whole square plus 30 P1 plus 10. Okay, C2 will be 0.05 P2 whole square plus 10 P2 plus 10. Okay, so that is what my C1 and C2 are equals to. So now, right, more things are there. So total power demand PD is 200 megawatt, and the limits are given to me. Okay, limits of individual plants are given. Determine the power output of machine 1 and machine 2 that satisfy the demand for minimum cost. So what is the condition for minimum cost? My incremental cost of 1 and my incremental cost of 2 must be equal. So what is the incremental cost of 1? That is 0.01 into 2p1 plus 30 must be equals to 0.05 into 2 plus into 2p1 p2 plus 10. Okay, so from here I can say what will be the values. So this will be 0.02 so I can divide by what I can divide by, I can divide by 0.02, right? I can divide by 0.02, that will come out to be P1 minus 5P2 equals to, I can see divide by 0.02. So what is 0.02? 2 by 100, 1 by 50, so it is 50, right? So that 30, okay, that 30 will go there, minus 20 into 50 is minus 1000. So minus 20 into 50, yeah, minus 20 into 50 minus 1, yeah. So I can rewrite this 5P2 minus P1 will be equals to 1000. Okay, so yeah, and also there is another constraint. What is the other constraint? My P1 plus P2 will be equals to 200. Okay, so if I add these two equations up, right, so I will get my 6 P2 equals to 1200 megawatt. So my P2 will be equals to 200 megawatt. Now is it within the range? No, actually maximum value of P2 is 180 megawatt, right? So I cannot like this is out of range. This is even greater than the P2 max, right? So in this case, what I will do, I will choose the maximum value of P2. I'll choose the maximum value of P2, right? Okay, so I will have to choose the maximum value of P2. What is the maximum value of P2? Maximum value of P2 is 180. Okay, and then what will be the P1? What will be the P1 value? If P2 is 180, P1 value will be 20. P1 will be 20 megawatt. Now, the thing is that how are we actually finding this, like how are we choosing P2 to be 180 and P1 to be 200, right? How are we choosing this? For this, we have to understand what is the incremental cost value, IC1 or IC2. If it is like if we meet the condition of economic load dispatch, we know IC1 will be equals to IC2, right? Both of them will be equal because we have equated them, right? We have equated them. If we choose my P2 to be 200 megawatt, but we will not be able to choose, but let's say hypothetically if I am able to choose P2 equals to 200 megawatt, then what will be my IC1? So P1 will be in that case 0, right? So IC1 IC2 will be 30 rupees per megawatt hour. And what is the IC2 and IC1 here? Here we are not actually meeting the condition of economic load dispatch, but let's still calculate IC1 and IC2. What is the IC2? IC2 will be, I will just put it in the formula. So 0.05 into 2 into P2, we have calculated the value of P2, that is 180 plus 10. So that is 28 rupees per megawatt hour. Okay, my IC1 will be, in this case, if my sorry, it is not 200, sorry, 220, right? It is 20. If P1 is 20, then it will be 0.01 into 2 into 20 plus 30, so it comes out to be 30.4. So but here, right, after calculation we are seeing that incremental cost of 2 is 28, it is 30.4. So basically what I did, incremental cost after equating both were actually coming out to be 30, right, with most economic condition. Now which one shall I choose? Which one shall I increase? Basically in this case I chose P2, and in this case I chose after choosing P2 I saw that the overall incremental cost will actually, this will be 28 and this will be 30.4. So like which one shall you choose? Which one shall you choose to go to the upper limit or lower limit, right? Because intuitively I told you that actually we want 200 megawatt, but my upper limit is 180 megawatt. So I have to choose, like economic condition is telling me that we have to choose the highest value of P2, but I will not be able to choose the highest value of P2. I have to choose the maximum value, that is 180, the maximum allowable value. So intuitively how you can understand that which one shall you choose? You can understand this by assuming if they were actually providing equal load, right? Let's say my demand PD is 200 megawatt, right? And if I assume that P1 is equals to P2 equals to 100 megawatt, right? Then what does my incremental cost of C1 of 1 and incremental cost of 2 becomes? So in this case, what is my incremental cost? Incremental cost of C1, right, that is equals to, if it is 100, 0.01 into 2 into 100 plus 30, that is 32. This is 32. Don't worry, I will summarize again. Don't worry, don't take the stress. I will summarize this hour. And incremental cost of 2, right, will be equals to, if both of them are delivering the same power, that is 2 into 0.05 into 100 plus 10, it is 20. Now tell me that if I increase the P1 value, let's say P1 will supply more power, it has more incremental cost. With increase in power generation, the cost is higher here, right? P2 has only 20 rupees per hour cost, that is by increase in certain power generation of P2 of the generating station 2, the cost is only 20 rupees. Incremental cost is only 20 rupees. So there is only 20 rupees of increment extra cost I need to provide, right? So this will be in megawatt hour, right? Sorry, megawatt hour. My unit is wrong. This will be in megawatt hour, not cost, right? So which one will you increase actually? Per megawatt hour increase in generation power energy generation. This is costing me 32, this is costing me 20. Which one will you choose? You will choose the second one. So that's why we maximize the second one. And anyways, from the equation also you can intuitively understand that economic condition is telling me to get to 200 megawatt. P2 should be 200, but I will that is out of my range, because maximum the plant 2 can generate is 180 megawatt. So I will maximize the P2 because P2 has the lowest incremental cost out of the two. So that's why you will always choose the lowest incremental cost. Lowest incremental cost. So what is the condition? Condition is like right now here where there were only two plants, so it was easy. But when there will be multiple plants, then how will you maximize? So we will maximize those plants which will have the lowest incremental cost, right? And we will minimize those which will have the highest incremental cost. So basically, if let's say I'm taking a hypothetical example, let's say my P2 is greater than, now first of all this condition will be only be triggered when we are going out of range, okay? This condition will be triggered only when we are out of range. I hope you understand what is out of range, right? So I will take a hypothetical example. Let's say I have three plants, right? P1, P2, P3. Now my IC1 of 2 is the lowest, then I have IC of 3, then I have IC of 1, okay? And how will you find out these ICs? You will find out these ICs at when these ICs are found when they deliver load equally, when they deliver load equally. Then what you will do, as this will be the lowest value, first you will maximize this will be maximized P2 max, right? Then after that you again calculate P1 and P2, right? P1 and P3, and then see that whether you are able to meet the load demand. If you are not able to meet the load demand still, then you will go to this. Only if your overall power, right, whatever you have generated is less than the load demand, then again here your P2 is already max. You will maximize your P3 also you will maximize, okay? P3 also you will maximize, and this should be enough. But even if this is not also enough, then you have no other option. You have to maximize all three, P1, P2, P3, okay? So I hope that's how you will solve these kind of questions when you are reaching a constraint. Intuitively I have told you how to understand this, and with mathematics also I have proven it to you how can we minimize our cost production. So that's it for this lecture. In the next lecture we will study in the economic load dispatch with losses in the line. Thank you and happy learning. Hi everyone and welcome back to PrepFusion. So today we will start with the second part of this economic load dispatch. So today we will discuss about economic load dispatch with losses. Also we will do the few gate FAQs that came from this topic, economic load dispatch, right? So this is the first one that came in gate 2014. Let's solve this. The fuel cost function of two power plants are given. Okay, cost functions are given. PG1 and PG2 are the generated powers. A and B are just constant. If the two plants optimally share 1000 megawatt of total power at an incremental fuel cost of 100 rupees per megawatt hour, the ratio of the load shared by the plants P1 by P2 will be. So they are given me that they are sharing the load optimally. If they are sharing the load optimally, that means incremental cost of 1 will be equals to incremental cost of 2. That is from the Lagrange's equation, right? This 2 has to be equal, right? And that is given to me, that is given to me as 100 rupees per megawatt hour. And they are asking me what is the ratio of the power delivered by plant 1 to power delivered by plant 2. So what is IC1? IC1 will be differentiation of the cost function with respect to its own power PG1. So it will be 0.05 into 2 PG1 plus A. Okay, and your IC2 will be equals to 0.2 PG2, or I can directly say P1 P2 only, plus 3A. Okay, and this will be 0.1 basically, sorry, 0.1, yeah. Now they have given me that both of them are sharing a total load of 1000 megawatt. So this will be equals to 1000 megawatt. Now I have to equate these two, right? I have to equate these two. So if I equate these two, what do I get? If I equate these two, I will get this value, that my 0.1 P1 plus A will be equals to 0.2 P2 plus 3A, right? So from here, if I multiply by 10 on both sides, this will be P1 minus 2 P2 is equals to 4A. That is what my P1 minus P2 is. Now what I can do is I can subtract these two equations. If I subtract these two equations, right, I will get that my 3P2 equals to 1000 minus 4A. Okay, 3P2 equals to 1000 minus 4A. Now P2 will be equals to 1000 minus 4A. Okay, 1000 minus 4A divided by 3. But will that help me? That will not actually help me. Okay, but let's not go into this, right? Let's not go into this. Actually, let's not go into this. So they have to given me, right, what is the incremental cost, that is 100. So this will be equals to 100 actually. This will be equals to 100. Okay, so my 0.1 P1 plus A is equals to 100. So I can say if I multiply by 10 on both sides, it will be P1 will be equals to 1000 minus 10A, and your P2 will be equals to what? P2 will be equals to okay, that is also equals to 100. So if I multiply by 10, then I have to divide by 2. So this will be 1000 minus 30A divided by 2, right? That will be equals to, I'm just equating the incremental cost of the second one, 500 minus 15A. So what is P1 upon P2? So what is P1 plus P2? So P1 plus P2 is given to me, that is equals to 1000 megawatt, or I can say P1 plus P2 will be these two values, right? This plus this, so that will be 1500 minus 25A, and I already know what is P1 plus P2. P1 plus P2 is 1000, right? So P1 plus P2 is 1000. So from this my 25A will be coming out to be 500. So my A will be 20. And what do I have to find out? I have to find out the ratio of P1 over P2. So it's just simply you have to solve the equation, that's it. You simply have to be good at solving equations. So P1 by P2 will be 1000 minus 10A divided by 500 minus 15A. So this will be 200 minus 2A divided by 100 minus 3A, and A value is 20. So 20, this will be 160 divided by 40, that is 4. So P1 by P2 will be 4. This will be your answer for the question. You just have to be good at solving equations. Basically what I did was, I know my IC1 equals to IC2 equals to 100. So this is my IC1 that I equated to 100. Then I got this equation for P1, and I know my IC2 is this value, right? I equated this to 100. So from here I will get another equation, that is P2 equals to 500 minus 15A, and I know P1 plus P2 is given to me, that is 1000. So I will do P1, I will add these two equations. So which will be equals to 1000 equals to I will add these two values. From here I will get the value of A, and my P1 over P2 ratio will be this. P1 is this value, P2 is this value, and from there I will be able to find out the ratio of P1 and P2. Let's solve the next one. Okay, the incremental cost curves is given for both the generator A and generator B. Okay, the maximum and minimum generation limits are also given, like these are my limits, right? I can minimum generate 200 megawatt, maximum 450. Here it is 150 and 400 megawatt. The optimal generation schedule will be, what will be the optimal generation schedule? So optimal generation schedule will be when the incremental cost of generator A is equals to the incremental cost of generator B, that is the optimal cost schedule, right? So for that I have to find out the incremental cost of A and B. They are delivering a common load of 700 megawatt. So my demand is 700 megawatt, right? So what is my equation for incremental cost of generator A? The equation for incremental cost of generator A, this is y2 minus y1, that is 150. Like I will write down the equation of this line. Slope is 150 divided by 250, right? So it will be 3 by 5. 150 divided by 250, so it will be 3 by 5. So that is what my slope is into P1 plus the y-intercept. What will be the y-intercept here? So I have to, okay, for this, right, I will write the equation, that is like my incremental cost IC1 equals to 3 by 5 into P1 plus C1, I mean any constant value, right? What is a constant? Any alpha 1. Okay, so when my P1 what happened? When my P1 is 200, my incremental cost is 450, right? So 450 equals to 3 by 5 into 200, that is 200 plus alpha 1. So my alpha 1 will come out to be, this will be 5 into 40, 120 will go there, so it will be 330. So my alpha 1 will come out to be 330. Okay, so this will be my incremental cost of A. What about the second one, right? I am just finding out the equation of a straight line. I hope you know how to find out the equation of a straight line. IC of B. IC of B will be, what is the slope here? Change in Y. Change in Y is how much? It is again 150. Change in X is, this time it is 250. Same slope. Slope is same, but the starting points are different. So it is change in Y upon change in X P2, but the starting and ending points are different, right? So I have to find out the, again, the Y intercept here, right? This is the Y intercept. What will be the Y intercept? IC2 equals to, remember your slope is 3 by 5 into, this is like, sorry, B, right? All this is A A into B plus alpha B. So this will be equals to, so when my input is 150, when my power is 150, right, the cost is, incremental cost is 650. So 650 will be equals to 3 by 5 into 150 plus alpha B. That is what I have to find out. So alpha B equals to, so yeah, so my, this will be 50, right? 50, sorry, yeah, 30 into 3, 90, 90 will go there. So it will be 560 will be the alpha B. So this will be 560. Okay, so my incremental cost A and incremental cost B we have found out. Now is this absolutely correct here? Change in X is, yeah, generator B is, it is 250 and this is 150, right? Yeah, 250 by 150, 3 by 5. So it is same, it is exactly the same, there is no difference, correct? Yeah, okay. So uh, when will the, so for most economic condition these two must be same, right? So demand is 700 megawatt, that is P1 plus P2, correct? So that is one equation. Other equation is this one, which I will equate these two. So if I equate these two, so basically it will be 0.6 P1 plus 330 equals to 0.6 P2 plus 560. So my P1 minus P2 will be equals to, this is 230, right? Yeah, 230 divided by 0.6, 230, yeah, 230 divided by 0.6, that is my P1 minus P2 equals to, right? So I will add these two up. What is 230 divided by 0.6? That is equals to 383.33. Now if I add the two equations, this is equation 2, right? If I add the two equations, it will be 2P1 will be equals to plus 700 divided by 2. So P1, right, P1 becomes 541.67 and your P2 comes out to be 158.33. But there is a problem. There is a problem. What is the problem? The problem is that here, right? The okay, is there a problem? No, where, oh, there is a problem, there is a problem. So my range of generator B, right, the lower limit of sorry, not 1 2, sorry, it will be AB, right? Okay, 1 to AB are same, okay, just you understand that. So lower limit of B, generator B is 150, but I am above the lower limit, so this is fine, generator B is fine. Whatever generator A, the upper limit, right, is actually 450, but it is telling that the we are crossing the upper limit 541, so I cannot go beyond, 450. So maximum generator A can service 450, okay. So I have to choose 450 and 250, that is the only option left, right? Because I cannot go beyond 450, right? 541 is the value for most economic load dispatch, but I cannot go beyond 450, so I have to choose 450 over here. I cannot go beyond this, and of course if I set my P1, so P1 is this value, whatever we are calculating is greater than P1 max, so my P1 will be set to 450, okay, and accordingly if my P1 is set to 450, then your P2 will come out to be 250. You can check with the incremental cost, you will find out that your incremental cost, right, for IC1 is the lowest than the incremental cost for IC2. That means you will first of all maximize the lower incremental cost, okay. So that's why you will maximize the lower incremental cost here, okay. So I hope that is clear. So option C will be the correct answer for this question. Now let's solve the next one. So next one, you have been given a fuel cost function of two generating units and the operating limits of both the units are given. Determine the minimum cost of generation for the given total power demand. Now the total power demand is spread over the whole duration of the day. So we are starting from 12 am and then ending at 12 pm. Now for this kind of load demand, what is the overall cost? That is what they are asking, what is the overall cost, right? So it's very simple. So when the load demand is 50, what will be the cost? We will find it out, okay. Determine the minimum cost. When the load will be 150, demand will be 150, then what will be the cost, and then I will ultimately find out the overall cost over a day, okay, cost over a day. So what is the cost in the case 1 when the demand PD is 50 megawatt. Here if the demand is in 50 megawatt, right, then what is the most economic load distribution? So if PD is 50 megawatt, right, so my P1 plus P2 will be 50 megawatt. So okay, P1 plus P2 is 50 megawatt. So what I can do is, right, now what will be the incremental cost function? So let me first write down the incremental cost function. What is the incremental IC1? IC1 will be 0. 048 P1 plus 8 and IC2 will be 0.08 plus P2 plus 6, okay. So I have to equate these two, right? So basically this shall be equals to, like, this will always be that case, right, when it is economically, like when the condition is economical, so this will always be the case. So for case 1 and case 2, this equation whatever we will find out, this will be always same throughout. So this shall be equals to this. So this will be yeah, so this value, right, I'll multiply by 0 point, divide by 0.08. I cannot divide by 0.08, but I can divide by 0.008. If I divide by 0.008, right, this will become 6p1, this will become 10p2, and this will be 8 divided by 0.008 and 6 divided by 0.008, yeah, minus 250. So I can swap these two up, but let me keep it minus 250 only, let me keep it, right. I can divide by 2 further, this will be 3p1 minus 5p2 will be equals to minus 125. So now, right, I will multiply this by 3p1 plus 3p2 will be equals to 150. So if I add these two values, what will happen? Sorry, if I subtract these two, right, then I will get 8p2 will be equals to 275. So p2 will be equals to 275 divided by 8. So which is 34.375 megawatt. Okay. So P2 comes out to be 34.375 megawatt. P1 comes out to be plus 50, 15.675 megawatt. Okay. So we got our P1 and P2. Now what we can do is we can actually find out the cost in the case 1. What is the cost in the case 1? How much cost it requires me to generate this much amount of power? So C1 will be equals to what? I already know the equation, right? I will just use the equation. C1 will be 0.024 into P1 whole square, that is 15.675 whole square. Remember, it is already your P1 is already in megawatt, right? P1 is already in megawatt, so you don't need to convert anything. Okay. Plus 8 into 1675 plus 80. And C2 will be 0.04 into 34.375 megawatt whole square plus 6 into 34.375 plus 120. Okay. So your 0.024 into 15.675 whole square plus 8 into 15.675 plus 80. So this comes out, your C1 comes out to be 211.297. Okay. And what will be your C2? We'll find out our C2. So C2 will be 0.04 into 34.375 whole square plus 634 plus 6 into 34.375 plus 120. So it is equals to 373.51.65. Okay, this is the cost. Now what is the total cost in the case 1? So total cost in the case 1 is this plus 212.297, it comes out to be 585.812. That is the total cost. So I hope that is clear. That is the total cost for the case 1. Okay, we'll find out now. This is cost per hour, right? Incremental cost per hour for the case 1. Okay, rupees per hour. I hope not incremental cost, sorry, overall cost per hour. I hope remember how it was cost per hour. Remember, cost per hour is there. Okay, cost per hour, rupees per hour. Okay, units are not given, but I hope you know it is rupees. Like in gate, units will be rupees per hour. Now, what about the case 2? For the case 2, my PD will be, remember, for the case 2, PD is 150. So these things will change just a slight tad bit. So my PD will become 150. This will become 150, right? And so your P1 plus P2 will be 150. So your 3P1 plus P2 will be 450 now. And already I have this equation. This equation is already with me, right? This will not change. Incremental cost will be same. Right? This also has to be equal for economic operation. Okay. So this will be, if I again subtract these two equations, I will get 8P2. Previously also it was 8P2. Huh? Yeah, 8P2. This will be 450, right? This will be 450. 8P2 will be equals to 600. Okay, I'm within the limits, right? 100 and yeah, I'm within the limits, 110. Previously I was within the limits. Let's see if now I'm within the limits or not. Okay, I did not check the limits actually. You should check the limits. 600. Okay, now we will anyways be out of the limits. Not possible, right? Delivering. Okay, no, it is 150. No, we will be within the limits only. So it will be not 600, sorry, 575. Okay, so 575 divided by 8, so it will be P2 will be equals to 875 megawatt. That is what my P2 will be equals to, right? So what is my P1 equals to? P1 will be equals to yeah, this subtracted by 150. So almost they are again within the range. My range was 70, between 10 and 100, right? So it is within the range only, so no problems. 78.125, they are almost sharing equally. What will be the cost? Again, the cost function will be like this same function only, but just instead of this, right, values will change. That's it. So I'll change the values over here. So here the values will now become this P1, right? P1 is what? 78.125. This will be 71.8125. So this will be so what will be the values basically? So this whole squared into 0.024 plus 8 into 78.125 plus 80. So this comes out to be 851.484 rupees per hour, and this will be 71.875 whole square into 0.04 plus 6 into 71.875 plus 120 757 0.89 rupees. Okay, so what will be your total cost in the case 2? Total cost in the case 2 will be 851.484. So this will become 1609.37 rupees per hour. Okay, so the thing is, so they have asked what is the minimum cost of generation for this total given of power. How will you find it out? So what will be the total cost per hour, right? That they are asking me. What is the total cost per hour, right? How will you find it out? So what is the total cost that was required in a whole day? Because after a day it will just keep on repeating, right? So in a whole day it will be CT1 for the case 1, and for how many hours was I operating at 50 megawatt for the first 6 hours and the last 6 hours. So for 12 hours I was operating at 50 megawatt, right? So what will be the total cost for this 12 hours? It will be CT1 cost per hour into the number of hours, that is 12. So it will be CT1 into 12, CT1 into 12 plus, right, what is the total cost in case 2, CT2? How much duration is it operating? It is operating for 12 hours, 6 am to 6 pm. So it is operating at 12 hours, operating for 12 hours. So this will be, okay, what is happening? My iPad is gone. Okay, CT1 into 12 plus CT2 into 12 divided by overall day. How many hours has happened? 24. So this will be the total cost per hour. Total cost per hour. Okay, so I hope this thing is clear. Rupees per hour. So this value will come out to be, we'll calculate this value. So CT1 was coming out to be, CT2 is this into 12 plus CT1 is 585.812 into 12 divided by 24. So it comes out to be 1097.6 rupees per hour. Okay, that is what your total cost per hour will be. Okay, I hope it is clear. Just we found out the average basically. Okay, so let's now solve the next question. The incremental fuel cost in some appropriate unit, right, for a power plant is given, right, for three plants is given, right, where P1 is the power in megawatt generated by unit I. I have 3 units. Assume that all 3 units are operating all time because all of them are on basically. Minimum and maximum loads on each unit is given. Okay, so the range of PI max and PI min is between 300 megawatt to 50 megawatt. Then if, just give me 1 second, if the plant is operating on economic load dispatch to supply a total power demand of 700 megawatt. So they are telling that the plant is operating at economic load dispatch, right? So demand is 700 megawatt and they are operating in economic load dispatch. That means their incremental cost must be equal to each other. The power generated by each unit will be, their incremental cost must be equal to each other. So all of them would be equal. So I see that incremental cost of 3 is constant, that is 30. So incremental cost of 3 is 30, so it has to be equals to 30 because it is not varying with load. So what is IC1? IC1 is 20 plus 0.3 P1. So IC1 is 20 plus 0.3 P1, that should also be equals to 30 for them to operate in economic load dispatch. So this will be 30 minus 20 divided by 0.3. okay, so this is actually coming out to be 33 point 33 33.33 megawatt. That is what my P1 is equals to. Okay, and what about my P2? P2, right? Again, I will equate the incremental cost of 2. Incremental cost of 2 is 30 plus 0.4 P2. 30 plus 0.4 P2 is equals to, it should also be equals to 30. So P2 basically comes out to be 0. P2 actually comes out to be 0. But that is not possible actually, because minimum is given at 50. So P2 cannot be equal to 0. That is not possible, right? P2 cannot be equal to 0. So we have to choose the minimum value of P2, because we have to choose the minimum value of P2. What is the minimum value of P2? The minimum value of P2 is 50 megawatt. So we cannot go below this. Also P1, right? P1 also minimum value is 50. So I cannot choose 33.33. That is not possible. Correct? Okay. So yeah, P1 is also 33.33. That is not possible. So I cannot simply use this equation for them to operate in economic load dispatch. So I have to find out the whose incremental cost is minimum. How do I find out whose incremental cost is minimum? One method I told you to divide the loads equally. Other way is to see what is the minimum value, right? And what is the minimum value of the incremental cost for each of them. So I see that IC1 minimum. What is IC1 minimum? IC1 minimum is when this value is minimum. When is this minimum? When this value is minimum, when P1 is minimum. P1 minimum meaning when it is 50. So if it is 50, right? So it will be 20 plus 0.3 into 50. So it will be 20 plus 15, right? Which will be equals to 35 megawatt. Okay, 35 megawatt. So this is the minimum. IC1 minimum. What is IC2 minimum? Sorry, not megawatt. Sorry, 31 rupees per megawatt. I think it will be in the unit will be some appropriate unit. Okay, we don't care about the unit right now. But the thing is, this is 35. So the minimum IC1 can be only 35, right? I cannot go below 35. So we have to choose this one only, minimum value of IC1. And what about IC2? IC2 minimum. What is the IC2 minimum? IC2 minimum is 30 plus 0.4 into P2, that is 30 plus 20, that is 50. Okay, so IC2 is minimum is 50. So first of all, I will what is IC3? IC3 is constant. So this, right, you cannot simply solve. You have to actually think a bit. So gate question, sometimes you have to think. IC3 is 30. So in which order shall I choose? So this will be not wrong anyways. Okay, which order shall I choose? First of all, I shall choose the lowest incremental cost. So IC3 is the lowest one. So this will get the highest priority. So this will have the highest amount of load. Okay, then I will choose my IC1 because this is lower, and then I will choose my IC2. Okay, that will be the order of priority. Okay, so IC3, IC2, then IC3, IC2, IC1, then IC2. Okay, so here, yes. Now P2 cannot have higher load. I cannot give P2 the higher value of load. P2 has to have lower load, right? That is one thing. Now Now this one is fixed, right? This one is the, sorry, okay, I wrote it opposite. IC3 is minimum, IC1 is minimum, then this is that, this is right. So this one is constant actually. Now I know this always, so the thing is the incremental cost the incremental cost of unit 3 is always lower than the incremental cost of other units for any load. So the thing, right, there is no fixed way to solve this economic load dispatch here, right? I told you that we can divide our load into by 3, right? Assume that they are sending in like equal power, equal incremental cost. It's not always the case. So like think in the question, okay? Incremental cost, it's not like always they will deliver the load equally. You have to think according to the question. Here I was wrong. You have to think according to the question. Okay, so yeah, so my incremental cost of 3 is always less no matter what, no matter what is the loading. So first IC3 will anyways get the priority. I will sort out about IC1 and IC2 later. Okay, so IC3 will, then that's why my unit 3 will deliver the highest load, whatever the maximum possible load that unit 3 can deliver, because its incremental cost is the lowest. So P3 max, P3 will be the maximum. P3 will deliver maximum load, which is equals to 200, sorry, 200 or 300, 300 megawatt. P3 will deliver maximum load 300 megawatt. So P3 will be equals to 300 megawatt. Now I will apply the economic load dispatch condition for the other two units, or you can find it out from here. P3 will be 300. Okay, P3 is 300 here, P3 is 300 here. Here P2 is the higher value, here P2 is a lower value. I will obviously, my option A will be correct because we have already found out that the minimum incremental cost of P1 is lower than P2. So P1 will deliver higher value of power. But still, let's prove it actually. Let's solve it numerically. Let's solve it. I know because we have found out that first priority will be to 3, then priority will be to 1, then priority will be to 2. So more loading will be given to 3, then bit lower loading will be given to 1, that we can see from here, and the lowest loading will be given to P2. That can be intuitively understood, but let's solve it. So first we have given the maximum possible load to P3, then this question gets converted into a question of two generating units whose power demand is 400 megawatt. How? We know that my P1 plus P2 plus P3 equals to 700 megawatt. Out of this, already P3 is fixed to 300 megawatt. So P1 plus P2 equals to 400 megawatt. So P1 plus P2 is 400 megawatt, and I know the incremental cost of 1 and 2 must be equal to each other, right? So this must be equal to each other, that is this value must be equal to the other one, that is this one. from here I can get P1 3P1 minus 4P2 equals to 100. Okay, and P1 plus P2 is 400. So 3P1 so this will be 7P1. If I subtract this, 7P1 will be equals to 1100, right? So P1 will be coming out to be, okay, something is wrong. Oh no, P1 is coming out to be lower. Well, how is it possible? So this goes there. It's 20 P1, right? Yeah, 20.0.3 P1. Yes, 20 plus 0.3 P1, 30 plus 0.3 P1. So this P1 will go on that side. 3P2 minus 4. So if I, oh sorry, I'm subtracting. This will be P2, right? What am I talking? This will be P2. P2 will be equals to 157.143 megawatt, and of course your P1 will be the other one, that is plus 400. So 242.85 megawatt. So from this, like intuitively also without solving, I told you what will be the answer. But of course now I hope with the answers you are able to see option A will be the correct answer for this question. Okay, now let's discuss about the next topic for the same chapter, that is economic load dispatch when losses are considered. So what is my target? My target is to minimize the total cost function, which will be basically summation of individual costs of individual plants as they are function of their power. Okay, now I have to minimize this. Now what will be my, this is the function that I have to minimize. Now what is the constraint? Constraint is my input power, whatever I am generating, I equals to 1 till n should be equals to the demand. Now there is an additional term, that is P loss, that will be a function, that will also be a function of Pi only. Okay, P loss is a function of Pi. So basically PL, where PL is a function of Pi, because I have multiple generating units. Okay, here I have a generating unit, right? 1 2 3 4, and then right, then there are few loads connected, right? So it does not matter, it does not, like I'm just drawing this roughly, actually it does not matter, right? Now it does matter that which one will send some power, so there will be some loss. So this loss will be function of the Pi, basically whatever, which plant, where is the plant situated. So this loss is basically function of Pi. Okay, so now again using the same Lagrange's formula, so this, right, I can further write, previously we had written it as Pi minus Pd. Now it will be basically I will be equals to 1 till n Pi minus Pd plus PL, sorry, minus PL. Remember, this is not constant. Okay, this is not constant. It is a function of the input generated power. This is constant. Load demand is constant. It does not depend on the input generated power, right? It is constant. Okay, just be careful. So now again I can write the same CT. CT will be what? CT will be equals to this whole thing. Okay, and this whole thing here, right? This side is 0, basically this side is 0, right? So this will be lambda times this, right, minus lambda times this. Okay, so again I will differentiate this equation. If I differentiate this equation, so dCt upon dpi must be equals to summation, or like for a single plant, right, it will be dc1 divided by dp1 minus lambda, this will be dp1, this will be 1 minus, now this will be 0, differentiation of pd with respect to pi will be 0, but this will not be 0, it is a function of pi, so this will be minus of dpl upon dpi, it will not be 0 anymore, this I have to make it 0, right. So basically what is happening is that my incremental cost is a separate factor, right, because incremental cost is not just lambda, it is equals to a separate factor. So from here I get the condition for lambda, what will be my lambda equals to, lambda will not be equals to incremental cost now, lambda will not be equals to incremental cost, lambda will be equals to 1 divided by 1 minus dpl divided by, this will be 1 actually, 1 here for ith load lambda I, incremental cost for I, right, previously this was simply 1 minus 0, so lambda was incremental cost, so unit of lambda is simply incremental cost, that is the unit of lambda, right, that is incremental cost. So lambda I, that is incremental cost of the unit I, right, will not be just lambda, now it will be 1 minus 1 divided by 1 minus dpl by dpi into dci divided by dpi, okay. So it is not just incremental cost, it is equals to, like, there is a factor, this factor is known as penalty factor, this factor is known as penalty factor of plant I, right, also called as li. So your lambda now becomes, lambda I becomes li into incremental cost of the plant I, okay, into ic of I, sorry, not ic of I, sorry, sorry, this will not be your incremental cost, unit will be same, right, because here I have power, here I have power, so now your lambda will not be simply equals to incremental cost, it will change, it will be equals to li into ic of I, okay. So this is what happens when losses are considered, okay. So like, what will be your PD function, how will your PD function look like, that is what we want to find out, right. So let's take a very simple example, let me take a transmission line with two generating units at both sides, okay. So if I take a transmission line, okay, then and let me assume that we have a load demand at the that is PD, okay, and through here this is unit 1, this is unit 2, so this is delivering P1 amount of power, I1 amount of current, right, and this is delivering I2 amount of current, okay, and all of them will have some resistance, right, so this much length will have a resistance R1, this much length will have a resistance R2, and this much length will have a resistance R3, okay. So what is the total power loss in the transmission line? So what will be the total power loss in the transmission line, P loss? It will be I1 square into R1 plus I2 square into R2 plus, through here how much current is flowing, I1 plus I2, right, I1 plus I2, so it will be I1 plus I2 whole square into R3, okay. So what is my I1 equals to? So I1 will be equals to what? I1 will simply be equals to power delivered P1, it's a three-phase system, so it will be root 3 V cos phi 1, okay. Whatever is the voltage level, generally we assume the voltage level to be constant, but let's assume that if they are, even if they are different, so I1 will be P1 divided by root 3 V1 into cos phi 1, I2 will be P2 divided by root 3 V2 into cos phi 2. Okay, so I can replace all these things over here, right? I can replace all these values over here. Let me, before that, let me simplify this thing. This will be PL will be I1 whole square into R1 plus R3 R2 plus R3 plus 2I1 I2 into R3. Okay, so my I1 square is basically this one, right? This whole square. So I will copy this, I square this. If I square this, right? Also remember one more thing, I forgot to remember that it's a single phase loss, right? But it's a three phase system. If it's a three phase system, don't forget to multiply by 3. So 3 will be there actually. 3 will be at the outside. So 3 will be here, 3 will be here, and this will become 6. Okay. So now this will be this root 3 VL cos phi 1 R1 plus R2. So this whole square into P1 square into R1. Like, I'm trying to come to a conclusion, don't worry, I will explain the conclusion just now. Into R1 plus R3. Plus 3 is also there, right? 3 is also there here obviously. Plus the same thing basically for P2. Same thing I can do for P2 as well. Plus 6 I1 into I2. So it will be basically R3 will be there, I1 I2 will be divided by 3 V1 V2 cos phi 1 cos phi 2 into P1 P2. So I'm trying to conclusion, right? I'm trying to a conclusion. So all this is a constant. This is a constant, right? This thing is a constant. This thing is a constant. Like this whole thing actually, R1 plus R2. I forgot to write the R1 plus R2 over there. Sorry. So how do I reduce the space here? Here I'll have R2 plus R3, okay, and yeah, this will be R3, right? Okay, so this is a constant, this is a constant, okay, so this will be basically, I can assume this to be a constant B11, okay, I can assume this to be a constant B11, and I can assume this to be a constant B22, and this, let's say it is B12. Okay, all this I can assume. So my loss is a function of B11, because these things will not vary. This is load, this is dependent on the load. V1 voltage across the terminal will not vary. Resistance of course will not vary. Only the input power can vary, right? So B11 into P1 square plus B22 into P2 square plus B12 into P1 P2. So now I hope it is clear that your loss function is a function of the power generated. Your loss function is a function of the power generated. Okay, so I can write my loss function in terms of two summations. Why? Because like this, right, this is a factor ij, so in terms of two summations I can write my loss functions. It will be basically, in this case I can write it as your pi into bij into pj, where my I goes from 1 to n and my j goes from 1 to n. So in this case, like, let's take the example. In this case, what is happening? In this case, if I put I equals to 1, j equals to 1, it will be p1 whole square into b11. If I put I equals to 1, j equals to 2, it will be p1 p2 into b12. Then I equals to 2, j equal to 2, it will be b22 p2 whole square, and j equals to 2, I equals to 1, sorry, I equals to 2 and j equals to 1, it will be p21 p1 into p2 into b21, and b21 and b12 are just will be symmetrical basically. So b21 plus b12 will become this, right? So this will be b21 plus b12, because this product is same, right? P1 into p2 or p2 into p1, both are the same thing. Okay, so now let's do another analysis. I know for economic load dispatch, for economic load dispatch, what needs to happen? For economic load dispatch, my Li, right, into the incremental cost, Li into incremental cost, sorry, Li into the incremental cost here. Li into incremental cost must be constant lambda, right? All of them should be same basically. Lambda I, this should be same across throughout. It has to be same. Okay, so Li into incremental cost I must be same, must be constant. Right? That is equals to lambda I, that must be constant. That basically means if my incremental cost is higher, then for it to be constant, my Li must be lower, right? So basically what it means is that, let's say for a particular plant, if incremental cost is higher, then its penalty factor must be lower. For economic load dispatch, basically this plant will be considered to deliver any power only if its penalty factor is lower, even though its incremental cost is higher. That means if I am increasing the load, I need to provide more input, that is there, but as if its penalty cost is lower, right, that means even though the incremental cost is higher, but there is lesser loss in the transmission line. So I can take two cases. Let's take two cases, right? Okay, just example case, like the same case only here, right? I have a 2 generator here, correct? So if I consider this case, let's assume that here the incremental cost of this plant 1 IC1 is equals to 10, and here the incremental cost of this plant 2 is equals to 20. But the penalty factor here Li L1 is equals to 0.5, or let's say it is 1, and here the penalty factor, right, L1 is L2 is 0.25. So then which one will be given priority? Although here the incremental cost is lower, but the product, right, is Li into L1 into IC1 is 10, and here it is L2 into IC2 equals to 5. So this one actually will be given priority. So 2 will provide more power, because even though its incremental cost, right, generating power cost is higher, but the loss is lower. So let's say if I'm generating 10 megawatt, I'm able to deliver 8 megawatt out of it. But here if I generate 10 megawatt, I'm only able to deliver 4 megawatt. So 6 megawatt is getting lost in losses. So even though the cost of generating 10 megawatt is lower, but most of it is getting lost in the transmission line. So it is not reaching the load. So it is not serving the purpose. It is not catering the demand. Okay. So that is why it is important to understand both the LI and the incremental cost. Okay. So I hope that is clear. Now we will solve few questions with this. So this was a GATE 2012 question. The figure shows a 2-bus system where demand is 40 megawatt here. Okay. The fuel cost is given to me. Cost function are given to me. Okay. Fuel cost is given. It is a constant fuel cost. The losses in the transmission line is given. So it totally does not depend on PG2. Why? Because it is directly connected across the terminal 2, across the bus 2. So there obviously will not be any loss from PG2. But you can see that the cost is higher than here. Cost is higher than the PG1, but still this can be good actually. We will see how the load gets distributed, where the loss coefficient is specified in per unit on a 100 MVA base. Okay, the most economic power schedule will be, what will be the most economic power schedule? So the cost functions are given to me. Okay, they are actually constants. If the cost functions are constants, okay, the cost functions are constants. What have they given actually? Actually, the fuel cost of generator G1. Okay. Megawatt hour. Okay, actually, right, this is not the cost function. They have given the incremental cost. They should have mentioned they have given the incremental cost. They have not properly mentioned, because I hope you remember what was the unit of incremental cost. It was dC upon dP, right? What was C? C was rupees per hour, and P is in megawatt or kilowatt, whatever, right? So basically this will be rupees per megawatt hour. So this is the unit of incremental cost. So actually they have not given you the fuel cost, they have given you the incremental cost. These are incremental cost. So what do I know? What we have we proven for economic load dispatch? My LC1 into IC1 should be equals to, sorry, L2 into IC1 should be equals to L1 into IC1 should be equals to L2 into IC2. Now what is L1? L1 is basically 1 divided by 1 minus del PL divided by del P1. So that is equals to 1 divided by 1 minus, so what is del PL upon del P1? It is 1 minus P1, right? You differentiate this with respect to P1, you will get this. What is L2? L2 is 1 divided by 1 minus del P1 by del P2, which is 0 basically, because there is no, like, my loss function does not depend on, the second generator. Okay, so it will be 1 minus 0, so it will be 1. Okay, so right now I can equate these things. So 1 divided by 1 minus P1 into incremental cost of 1, that is 10,000, right? 10 raised to power 4 equals to 1 into 12,500. So my P1 from here I can get the value of P1. 1 minus P1 will be equals to what? It will be 10,000 divided by 12500, so 0.8. So your P1 comes out to be 0.2 in per unit. Okay, P1 comes out to be 0.2 in per unit, remember. But they have given us the base. What is the base? Because this, right, is in per unit, remember. This is in per unit, base is 100 MVA. Okay, so you will multiply by the base. Your P1 will be 0.1, 0.2 into base. Base is 100 MVA. That is equals to 20 MVA. So 20 megawatt, 20 megawatt, sorry, 20 megawatt, right? So P1 should be 20 megawatt. So remaining should be sent by the PG2. Now remember this thing, we have a loss as well, right? Don't forget the loss. What is the loss? If P1 is 20, what is the loss? Loss is 0.5 into P1 square, right? Now currently, right, let me write this in per unit, then I will convert this into absolute. So PL per unit will be 0.5 into P1 per unit whole square, that is 0.2 whole square. So this into 0.5, 0.02. What will be PL in actual value? It will be into 100, right, which will be 2. So 2 megawatt will be the losses. So overall my P1 plus P2 must be equals to P demand plus PL. So P1 I know, that is 20, P2 I have to find out. And P demand is demand is 40 megawatt, right? Demand is 40 megawatt. Okay, demand is 40 megawatt plus losses is 2 megawatt. So P2 will come out to be 22 megawatt. That is what my P2 will come out to be. Okay, so that will be the answer for this question. P2 is 22, P1 is 20. So P1 is 20, P2 is 22. So option A is correct. Okay, option A will be the correct answer for this question. So let's now solve the next question. A power system has two generating plants with the power being dispatched P1, P2 equals to this. The loss coefficients are given. Okay, loss coefficients meaning this B11, B22, this, right? These are given. I hope you will be able to write down your P loss in terms of loss coefficients. B12, B22, B11 is given, B21 is not given. Okay, and they are asking you to find the penalty factor of 1 and 2. So what is the penalty factor of 1 and 2? Penalty factor of 1, right, is simply equals to 1 divided by 1 minus del P loss divided by del P1. For this I need to find out the loss function. What is my loss function? Loss function is combination of P1, sorry, it is B11 into P1 whole square plus B22 into P2 whole square plus, we derived it, B12 plus B21 into P1 P2, right? If you remember, that is what we derived here. It was B1 plus B12 plus B21. Now here, right, they have not mentioned anything about B21. So I will assume, if nothing is mentioned, right, about B21, assume B21 to be equals to B12. If they have not mentioned it, so your loss function gets converted into this value, right? To B11 P1, sorry, I will not differentiate it over here only. So like, yeah, sorry, your loss function gets converted into this value. This will become b12 plus b21 will become 2 into b12. This is what your loss function will become. Okay, so now right, now what will be your penalty factor 1? L1 will be equals to, my P1 and P2 are already given, right? What is P1? P1 is 150 megawatt, it is given to me, and P2 is 275 megawatt. Okay, so what is L1? L1 will be 1 divided by 1 minus del PL upon del P1. So if I differentiate, this will be 2 P1 into B11 minus 2 B12 into P2. Okay, that is what my L1 loss function will be equals to, which will be 1 minus 2 into B. What is B1? B11 is given to me, that is 0.1 into 10 raised to power minus 2, that is 10 raised to power minus 3 into P1. P1 is 150 megawatt. Remember, this is, the coefficients are in megawatt inverse, so automatically the megawatt inverse and megawatt will get cancelled. It will be unitless. Plus minus into B12. So what is B12? B12 is minus of 10 raised to power minus 4 into your loss, your power delivered, that is 275 megawatt. Okay, so your L1, I will calculate the value of L1. This will come out to be okay, plus 2 into 275 into 10 raised to power minus 4. This is plus actually minus 300 into 10 raised to power minus 3 plus 1, so 0.77, which comes out to be 1.3245. So in the two options actually 1.32 is given, 1.32 is here, 1.32 is here. What about the other part? Okay, what about L2? So L2 will be same, like same relation only, but the numbers will be different. 2 into P2 into B22 minus 2 into B12 into P1. So this comes out to be 1 minus 2 into B22. What is B22? B22 is 0.13 into 10 raised to power minus 2. 0.13 into 10 raised to power minus 2. Okay, and into P2, obviously P2 is there, P2 is 275. Then we have minus of 2 into B12. B12 is minus 10 raised to power minus 4 into P1, 100, so 150. Okay, so it will be 300 into 10 raised to power 4, minus minus becomes plus. Okay, then minus into 2 into 0.13 into 275 into 10 raised to power minus 2. I add this up, right, becomes negative, plus 1, then I take the inverse, this becomes 3.174. okay, 3.174, which is approximately 3.175. so option D is correct. The penalty factors we have found out, L2 and L1. So there is a part 2 of this question. Obviously this was the part 1. Part 2 is, if these conditions are there, now they are asking, they are telling to raise the total load on the system by 1 megawatt, additional cost is 200 per hour. to raise the total load on the system by 1 megawatt, the additional cost is 200 rupees per hour. What is it? So additional cost delta C is 200 rupees per hour for raising the load load demand to 1 megawatt. Now what is this ratio? Is this ratio something similar? Delta C by delta PD? Is this delta C by delta PI something similar to that, load demand or PI, whatever you want to write? So this is basically the incremental cost, right? Incremental cost of what? Incremental cost of the whole system. That is lambda actually. Incremental cost of the system, not just planned one, incremental cost of the whole system, right? That is equals to lambda. Lambda is the product of L1 into IC1. So it is the incremental cost of the whole system including the loss factor. So here they are, because they have told it is the incremental cost of the whole system, right? So lambda, if the loss was not there, lambda was equals to IC1, IC2, right? But as the penalty factor is there, so your lambda is incremental cost of the whole system including the losses. So we have to multiply by the penalty factor with L1, okay, which will be equals to L2 into IC2. Why this will be equal? Because they have told me in the question that they are operating in economic load dispatch. They are operating economically, okay, dispatch economically. So we will do that basically. So that is given to us, that is equals to 200 rupees per megawatt, which is equals to L1 into IC1 of plant 1. Because what are they asking? They are asking me to find the additional cost per hour to increase the output of the plant 1 by 1 megawatt. So basically I need to find out IC1, right? This is the incremental cost of the whole system including the penalty factor, but they are just asking me what will be the additional cost per hour to increase the output of the plant 1, only plant 1. So I am just discussing about plant 1, so I don't need to include the loss factor. So I need to find out IC1. I know L1, so my IC1, right? IC1 will be equals to 200 divided by L1. L1 is 1.324. That is what my L1 is equals to. So this value will be equals to, if I calculate this value, right, this 200 divided by 1.3245, so that is 151. So what will be the addition, like incremental cost of the whole system is 200, but additional cost to increase 1 megawatt of plant 1 is only 151, okay? So it will be 151, answer will be 151 rupees per megawatt hour. This will be the answer, okay? I hope it is clear. Let's now solve this next one. So we have in optimal generator scheduling across multiple power plants, minimum fuel cost is achieved only the incremental fuel cost of each plant is equal, the penalty factor is same, the ratio of incremental fuel cost to penalty factor is same, the product of the incremental fuel cost to penalty factor will be same. So basically L1 into IC1 will be equals to L2 into IC2 will be equals to lambda, the incremental cost of the whole system, IC of whole system. Okay, so this question was pretty simple. Let's now solve the next one. Delete this page. So the next question is this one. Two power plants interconnected by a tie line as shown. B11, the loss coefficient is given to me, right? For B11 is 10 to the power minus 3 and nothing else is given. So basically my overall loss PL will be only B11 into P1 whole square. This is the same question that GATE gave us, right? I think just exact similar question. So it will be 10 to the power minus 3. This is not in per unit, okay? This is in exact values. Okay. So loss coefficient is this megawatt inverse. Yeah. Okay. Into P1 whole square. Okay, power is being dispatched economically with plant 1 as 100 megawatt and plant 2 as 125 megawatt. Okay, so power they are telling me that P1 is 100 megawatt economically dispatched. And P2 is 125 megawatt. The penalty factors for the plant 1 and 2 will be, what will be L1? So L1 will be what? L1 will be simply 1 divided by 1 minus del PL by del P1, which is equals to 1 divided by 1 minus 2 B11 into P1, which is equals to 1 divided by 1 minus 2 into B1, 1 is 10 raised to the minus 3, P1 is 100. So it is 0.2, basically 0.811 divided, so 0.8 inverse, which is 1.25. Penalty factor for plant 1 is 1.25, that is present in only option B, and for plant B it will be 1. Why? So L2 for plant, right? B will be 1 divided by 1 minus del PL by del P2. It is not like, my PL is not a function of P2, so it will be basically 1 by 1 minus 0, which is 1. So that's why option B will be the correct answer for this question. Like, pretty simple, straightforward question. Okay, let's now solve the next one. So this one is kind of interesting. This question is actually interesting. Okay, so here a load center of 120 megawatt is given. Okay, derives power from 2 power stations by a 220 kilovolt transmission line of 25 kilometer and 75 kilometers. The 3 generators G1, G2, G3 each has a capacity of 100 megawatt. So maximum they can deliver 100 megawatt power and have identical fuel cost characteristics. That means basically their IC incremental cost will be same. IC1 will be equals to IC2 will be equals to IC3. Their individual fuel characteristics are same, so their incremental cost also will be same, but their loss factor will be different. L1 will not be equals to L2 and L3, but L2 and L3 will be equal. Why? Because if you see, both of them are situated in the same bus, right? So the loss factor for L2 and L3 will be same. Okay, but for L1 it will not be equal because it is situated much nearer to the load. It is situated much nearer to the load, so it will have lesser loss factor. Their incremental costs are same, but L1 will have lesser loss. So what will I prefer? I will obviously prefer my generator G1 to deliver most of the load. I will obviously prefer my generator G1 to deliver most of the load. So they are asking me the minimum loss generation schedule for supplying 120 megawatt would be. Okay, so I see in option A that P1 is delivering 80 megawatt of power. Okay, in option B P1 is delivering 60 megawatt of power. In option, all other option, right, P1 is not the highest value. In here also as well, P1 is actually highest. P1 is actually higher value. Okay, here also P1 is highest, here P1 is same, here P1 is lower. So these two options are anyways eliminated because I know my incremental costs are same for all of them. Whichever one will have the lower penalty factor, through that generating station I would want to deliver the maximum power. So this generating station is situated much nearer to the load, so obviously I would want G1 to deliver the maximum power. So either option A can be correct or option B can be correct. Okay, either option A can be correct or option B can be correct. Now which one shall I choose? Shall I choose this one or this one? So I would actually, the better would be to like we can calculate the losses. Of course we can calculate the losses, right? But you can calculate like which one will have higher losses, but I'm not getting into that. I'm observing P1 should be P, because my delta is what, lambda is what, lambda is Li, lambda will be equals to Li into IC1. Okay, I want my incremental cost to be lowest. My IC1 is constant, fixed, right? It does not depend on anything. All of them have identical fuel characteristics, right? So I want my Li to be lowest. When will Li be lowest? If you remember your coefficients, right, it is I square into R, right? Wherever this R will be lower, losses will be lower, right? And what is R dependent on? R is dependent on rho L by A. So wherever L will be lower, the losses will be lower, right? So I would definitely want my plant P1 to deliver most of the power and most of the losses. So that's why here option A will be correct. Okay, I would want my plant P1 to deliver most of the losses and most of the power. Okay, because basically what will happen, it will deliver the power 80 megawatt to this load and the additional losses that will cater for this amount of power loss here. Okay, P2 and P3 will not deliver the additional loss. Okay, so like that's how intuitively you can solve. Of course, like this, in solutions as well, they will give you this reason only, that resistance will be lower for the P1. So P1 has to be the highest value. It will send most of the losses and it will send most of the power. Okay, I hope that is clear. So yeah, that's it basically for this lecture and this chapter, economic load dispatch. In the next chapter, we will study overhead transmission lines. Thank you, and I will see you in the next lecture. Until then, happy learning.